Okay. Is my audio clear? Just let me know if my audio is clear. Yeah. Okay. So we'll continue from where we left off yesterday. So in the yesterday's session, it was mainly about coordinate geometry as well as vector calculus. They are the foundations that are very important for us in order to proceed further in this course, which is EMF. So yeah, we'll proceed from the yesterday's topic. Yeah, we'll start with now electrostatics. In electrostatics, we are having basically 4 quantities. Electrostatics is all about understanding what are these quantities for various kinds of charge distributions and what are the relations between all these quantities. Okay, those 4 quantities are, first is electric field intensity, and the other name given for electric field intensity. In exams, sometimes you don't see this term as electric field intensity. So this is also called as electrical stresses. Other names are basically, we have, these guys called as electrical stresses, or also known as potential gradient. We also call it as potential gradient. Okay, and the units of this quantity is basically either volts per meter. How do you recognize this quantity? Okay, either the units of this quantity is volts per meter, or other units for this quantity is newtons per coulomb. And what is this electric field intensity? Any intensity basically measures the strength of the field, and this is defined as force acting on a particular charge per unit charge. Okay, so in short, you can say force per unit charge is nothing but electric field intensity, and hence the expression of electric field intensity is given by E bar is equal to F bar by Q, where F bar is nothing but force acting on the small q charge divided by the charge value itself. And from this, if I ask you what is the force acting on any charge, so that is given by F bar becomes equal to here from this. Okay, so we can write F bar as nothing but this is equal to Q times E bar. Okay, so this is also same as Q times E bar, right? So this is regarding the first quantity. Second quantity is electric flux denoted by phi E. So this is the total number of flux lines crossing a given surface. Okay, and flux is nothing but a scalar quantity. So this electric flux is scalar quantity, whereas the field intensity, flux density, these 2 quantities are nothing but the first and the third quantities are basically vector quantities. And the units of electric flux is same as units of charge. So this guy has units of coulombs. Okay, so this has the units of coulombs. Okay, next is flux density. Flux density is nothing but total flux lines that are crossing a given surface per unit area. So this is flux per unit area simply. Okay, and the units of this is nothing but, yeah, as you can see, units of flux by units of area. Units of area is nothing but meter square, and hence this is coulombs per meter square. And the other name given for electric flux density is also called as electric displacement. So wherever in questions you see electric displacement, they are actually talking about electric flux density is what you can understand. So this is also known as electric displacement, other name. Okay, and the last quantity is nothing but electrostatic potential. Electrostatic potential is another scalar term. So this is also known as electrostatic scalar potential or simply scalar potential. In electric fields, when they say scalar potential, they are talking about only electrostatic scalar potential. And it is nothing but work done per unit charge in placing the charge at the point of interest when brought from infinity basically. In short, you can say work done per unit charge means V becomes equal to V, potential V becomes equal to W by Q. Okay, and the units of this electrostatic potential is nothing but volts. I use the notation of V. Sometimes you also see it as phi, chi, depends on the examiner. So they may use other symbols for this particular potential, but I will be using the notation of V all the time. But sometimes it's also denoted as phi or chi, etc. Okay, so these are the other symbols you are having for potential. Okay. Yeah, so this is regarding the 4 basic quantities we are having. And furthermore, what is the relation between flux as well as flux density? For example, 2 relations you have to know here, flux as well as flux density. Obviously, both of them will have proportionality relation, and furthermore, flux is equal to flux density into area. You can directly multiply them if at all the flux density is constant. But if the flux density is not constant on the given surface, so we have to perform integrations. So that is nothing but phi e becomes equal to integration of d bar dot ds bar. So this is nothing but electric flux crossing the surface S due to the flux density term, which is nothing but d bar. And the other relation is nothing but d or d bar becomes equal to epsilon times E bar, wherein the flux density as well as field intensity both are proportional with respect to each other. And at least for the case of isotropic as well as homogeneous medium, in our course, if nothing is mentioned, we can safely assume the medium to be isotropic and homogeneous. So in that case, yeah, they have a proportionality relation, and d bar is given by epsilon times E bar. And we all know that epsilon becomes equal to how much? This is epsilon naught times epsilon r, where epsilon r is relative permittivity, or also known as dielectric constant. So the name given to this guy is dielectric constant, okay, or also known as relative permittivity. Okay. Now this epsilon naught, okay, we take the value of epsilon naught to be equal to, this is permittivity of free space, ability of the free space to allow the flow of electric flux, and this value becomes equal to 10 power minus 9 by 36 pi. Sorry. You can always use this data, that instead of taking it as 8.85 into 10 power minus 12, for calculations it becomes very easy for you whenever you take the data as 10 power minus 9 by 36 pi. Okay. So, and units anyway is nothing but in terms of farads per meter. Okay. So this is regarding epsilon naught as well as epsilon r. Okay. Yeah. Yeah, electric flux is coulombs, volts per meter is for electric field intensity or the strength of electric field. Okay, so this guy is having units of, because this is potential gradient, E bar is nothing but potential gradient, means what? You are taking gradient of potential. What is the units of gradient? Units of gradient is meter inverse, and what is the units of potential? Volts. So volt into meter inverse is nothing but volts per meter. That is the units of electric field intensity, not electric flux. Okay, electric flux has the same units as compared to that of, charge, right? Yeah, next. Next, coming to the different types of charge distributions, we are having mainly 4 types of charge distributions. Even in the syllabus, if you see, examiner has clearly mentioned the 4 types of charge distributions: line, point, surface and volume. Only thing is, point we are dividing it into 2 parts. One is nothing but point charge and second is group of point charges. So next is nothing but line charge. In case of line charge, we have a parameter known as line charge density. So this guy is known as basically, so this is known as the line charge density. Having units of coulombs per meter. So for 1 meter, how much amount of charge you are having? You are having rho L coulombs of charge. So that is the meaning of rho L coulombs per meter. And in case of surface charges, you are having something called as rho S. Rho S is nothing but surface charge density. So this is surface charge density. How much amount of charge you are having for every 1 meter square of the charge distribution. Okay. So surface charge density. Having units of coulombs per meter square. Okay. Charge per unit area. And lastly, we are having rho V, the important of all 3, relatively important of all 3, which is nothing but the volume charge density. So this is basically volume charge density. Okay. So which indicates for 1 meter cube of volume, how much amount of charge we are having? That charge is equal to rho V coulombs of charge. Okay. So in the first case, in case of line charge distribution, if at all we want to find out the total charge, we find out the total charge by simply performing line integration here, integration of rho L dl on the entire path where the charge is distributed. Second case, if I want the total charge in case of surface charge distribution, then the formula is nothing but integration of rho s ds obviously, and the integration is performed over the entire surface where the charge is present. And here in the last case, if at all I want to find out the total charge in case of a volume charge distribution, the formula is nothing but integration of rho v dv, and you are integrating this over the entire volume where the charge is present. So this is the expression for total charge. And in case of point charge, if I ask you what is the total charge, it is simply q, one single point charge you are having. And if you are having n charges, n point charges, and you want to find out the total charge there, this is nothing but summation of qi, okay? Summation of qi is nothing but the total charge, right? Yeah, yesterday's PDF and today's PDF I wanted to share together. I'll do it after this session. I'll share both the PDFs together. Okay. Yeah. So let us look at a few problems initially on the charge distributions. Okay. That is total charge calculations. So here in this question there is a charge density given to us, rho v. Okay. Units, if you verify, coulombs per meter cube means this is nothing but volume charge density. It's also given to us in the question itself, volume charge density. And this volume charge density exists only for what region? Only from 0 to 3, when r changes from 0 to 3. So means you are having, if nothing is mentioned, I can assume that this r is nothing but spherical, charge distribution. So this is nothing but, I can assume this is nothing but spherical coordinate system if nothing is mentioned. So you are supposed to find out net charge within the surface of r equal to 1. See, please notice that in this case, even though the charge is present up till 3, you are supposed to calculate the value of charge up till only 3, okay, or up till only 1 meter, okay. So here, what is the formula for total charge, at least in the given region? The formula for total charge, Q total is nothing but integration of rho v dv. Yeah, now again, rho v, examiner gave you, rho v is equal to 1 by r square, okay, into dv. Now we have to take dv in terms of spherical coordinate system. In spherical coordinate system, what is dv? dv is nothing but r square sine theta dr d theta d phi, okay. So 1 by r square as well as r square is gone, and then if you do the remaining calculation, you have integration of dr is nothing but r, integration of sine theta is minus cos theta, integration of d phi is phi. Now limits. Limits, if you notice, we only have limits for r. What is the limits for r? Limits for r is from 0 to 1. Okay, because of this one, I am taking the integration only from 0 to 1. And limits for theta and phi are assumed to be known to you. 0 to pi is the limits for theta, theta, and for phi it is nothing but 0 to 2 pi. And when you substitute the values here, then what is the answer you get? So 1 minus 0 is nothing but 1, and this is nothing but 2. Cos pi minus of minus is plus, cos 0 is 1, minus of minus 1 plus 1 becomes equal to 2, and the last one we have is nothing but 2 pi. So overall answer becomes equal to 4 pi. Okay, overall answer is 4 pi. Now I want to ask you one question. Here. What is the charge within let's assume this is a question. Please tell me what would be the answer here. How much is the charge within r equal to 4 meters? Within the surface of r equal to 4 meters. Don't be hasty. All are giving hasty answers. Please look at, not at, within. I am asking within. So you have to visualize how the charge is placed basically. You have to visualize how the charge is placed. Okay, 0 is not the correct answer. Rohan and Priya, to both, 0 is not the correct answer. Good, good. Manasvi, Pavani, good. Now, anyone else? 16 pi. Anyone got 16 pi? Okay. See the previous question, this question, if you notice, okay, this is the total charge distribution. But what do I want? I want how much amount of charge we have only in this region. Okay, I want how much is the charge we have only in the enclosed region, in a smaller region basically, only in this region. So the first question was this charge. How much is the charge that we have within this region of how much radius? Of radius of r equal to 1 meter. Okay. Now what do I want? Now I want a bigger, I have taken a bigger in fact sphere. What radius now? Radius is nothing but 4. So if you notice from 0 to 4 we have 0 charge. No, at r equal to 4 we have 0 charge. But rather if you notice from 0 to 3, don't you think we are having some charge? Yes. So because of that, in this problem what happens is nothing but, the total charge q becomes equal to integration of rho v dv only. But the limits of r will be from 0 to 4. Will be from 0 to 4. Okay. And you can split that into two parts. 0 to 4 integration means what? This becomes equal to integration from 0 to 3, where we have charge density. And from 3 to 4, outside 3 greater than 3, how much is the charge density? That is nothing but 0. So this is nothing but again rho v dv. Okay. Now what we do is nothing but, this value from 0 to 3. Okay. From 0 to 3, what is the expression? The expression is nothing but 1 by r square, and beyond 3 the value of rho v is nothing but 0. So now whatever integration you are doing, it's only done from 0 to 3, and hence again sin theta, d theta, d phi integration now also becomes equal to 4 pi only. So 4 pi into, for r the limits will be from 3 minus 0. So while when you do the calculation like in the previous case, you get the answer as nothing but 12 pi coulombs. Okay, so the answer would be 12 pi coulombs. Is that clear? Yes, good. One person got 16 pi. 16 pi would be the wrong answer because you are not even looking at these limits. You have to look at these limits. Where do you have charge? Charge is present only up till 3. You don't have charge up till 4. Okay, 3 to 4 it is empty. 3 to 4 you don't have any charges. So because of that, even though the original integration is done from 0 to 4, now you are splitting them into two parts, 0 to 3, 3 to 4. 0 to 3, this is the expression. 3 to 4, the value is nothing but 0. You are taking 0 there. Okay. So be cautious. These are the small, fine points you are supposed to notice while answering questions in exam. Okay. Nice thing is whenever you draw this diagram, it makes much more sense for you. The problem makes much more sense for you. So silly mistakes you can avoid. Okay. Yeah. Next, one of the most important laws we are having in electrostatics is Gauss law. So Gauss law is important from two viewpoints. One is nothing but, it will give us one of the Maxwell's equations, and the second is it also gives us the relation between the charge density as well as also the flux density. Okay. So from exam point of view, we have got a good number of questions on this formula. This is the ultimate formula. It is important in case of Gauss law. Okay. And apart from that, we also use Gauss law to find out electric field intensity expression as well as flux density expressions for some of the common symmetrical charge distributions. So wherever there is a symmetrical charge distribution, we can use Gauss law to find out the expression for E bar and D bar. Ultimately, the goal of this chapter is nothing but to find out the expressions of E bar, D bar, potential as well as flux for some of the common charge distributions. Okay. Anyway, so Gauss law says that whenever you take a closed surface, the flux coming out of the closed surface becomes equal to the charge enclosed inside that closed surface. That is what Gauss law says. So let's assume randomly you have taken some closed surface, random closed surface. This is okay. And I want to calculate how much is the flux coming out of. Okay. So this is basically some randomly shaped closed surface. and I want to calculate how much is the electric flux coming out of this closed surface. Okay. Who produces electric flux? Charge only, no? So coming out is nothing but phi E, and that phi E coming out of S. Okay. So this phi E coming basically out of S, out of what is closed surface S, closed surface S. Now this becomes basically equal to the charge enclosed inside S. Okay. So that becomes equal to basically the charge inside S. Charge enclosed by S. So in short form, Gauss law simply says that outcome is equal to source. Okay. So in simple terms, Gauss law is nothing but this is outcome, right? And outcome simply becomes equal to source. Okay. In fact, this is one of the questions that one of my students got in the recent BARC interview. So they simply asked, please explain Gauss law without stating Gauss law. Okay. So this was the question that they asked the person. So they wanted you to understand the Gauss law basically. So Gauss law simply says that, boss, stronger the source, more is the outcome. It's a very simple law. More is the stronger is the source, then more is the outcome that you are having because of that particular source. Electric flux is outcome, and that electric flux is because of charge. So larger the amount of charge, naturally more amount of flux can be produced. Okay. Yeah, mathematically put, what is flux coming out of any surface? Flux coming out of any surface is given by, earlier we have seen, integration of d dot ds. But since the surface is nothing but a closed surface, we are taking here closed surface integration. And now we have seen inside a closed surface we have a volume. Okay, and hence we are writing RHS in terms of volume integration. One more reason why we are writing RHS in terms of volume integration is, whenever I see a closed surface integration, I apply divergence theorem, and whenever we apply divergence theorem, so this expression which is integration of d dot ds now becomes equal to divergence of d bar integrated over a volume, and this is a volume integration. This is the volume that is enclosed by the closed surface. Okay, and since ultimately LHS became some volume integration, I am writing my RHS also in terms of volume integration. Okay, RHS, which was originally charge, in terms of volume integration is what? Integration of rho v dv. So that's what I have taken. This is integration of rho v dv, and since both are now volume integrations only, so I can equate the integrands. What are the integrands you are having? The integrand here is nothing but del dot d. Divergence of flux density becomes also equal to the charge density. So that's what we have, which is nothing but del dot d becomes equal to rho v, and this is also our Maxwell's first equation. This is also our Maxwell's first equation. We can also write that Maxwell's first equation in terms of electric field intensity by using the relation that, okay, d bar becomes equal to epsilon times E bar, and if you substitute this here, then assuming the medium again to be isotropic and homogeneous, we get the expression as nothing but del dot E becomes equal to rho v divided by epsilon. Okay, so this is basically the expression of Maxwell's first equation in terms of electric field intensity. Both are one and the same. So we call this as nothing but Gauss law in terms of differential form, which is also Maxwell's first equation. And this is again, this part as well as this part, both are nothing but the Gauss law in terms of integral format, or basically Maxwell's first equation in terms of integral format. And this is basically in the form of a statement: flux coming out of any closed surface becomes equal to charge inside that closed surface is nothing but in statement form. In short, for you to remember very easily, you can simply say ki outcome means electric flux. Electric flux is outcome here, that becomes equal to the source. Stronger the source, more is the outcome you are having because of that particular source. Okay, yeah, yes, let's now look at a few problems on this. Yeah, here concentric spherical shells of radius 2, 4 and 8 carry uniform charge densities of 20 nanocoulombs per meter square, minus 4 nanocoulombs per meter square and rho s respectively. So there are three concentric shells. Okay, there are three concentric shells. Let me show them. One is nothing but 2, 4, 8. So let's assume this is the smaller guy, 2. So these are the three shells. The first shell having a radius of how much? 2, and the second shell having a radius of 4, and the last shell having a radius of 8. On each of these shells, we have certain charge densities. How much is the charge density? One is nothing but 2 meter, one is nothing but on the inner guy 20 nanometer, second guy -4, and the last guy rho s. Okay, so here we have 20 nanocoulombs per meter square, and on the second guy -4 here, -4 nanocoulombs per meter square, and the last one is rho s. Okay, when the radius is 8, rho s, radius is 4, -4 nanocoulombs per meter square, and when the radius is 2, it is nothing but 20 nanocoulombs per meter square. So then we are supposed to say ki, the value of rho s is what? To ensure that flux density d bar becomes equal to 0, where at 10 meters. Okay, at 10 meters region, we have, the flux density being equal to 0. So let me show that, 10 meters line for you. Okay, so let's assume, so this is another region, 10 meters. And you have been told that at this 10 meters region, d becomes equal to 0. Okay, so d becomes equal to 0. Here, what I will be using is nothing but I will be using the Gauss law to solve this question, but I am taking the Gauss law in terms of integral format. Okay, let me call this 10 meters surface as nothing but S. Okay, it's a closed surface, all are spheres only. So when you apply Gauss law, on the closed surfaces, all are spheres, so all are closed surfaces. So then what do we get? Integration of d dot ds becomes equal to charge enclosed. Okay, but in this case, what is the value of d bar on the surface? On the surface, the value of d bar is nothing but 0. Okay, on the surfaces. The surface S is nothing but it's a sphere of radius 10 meters. Okay, and LHS because of that becomes 0. Means what? RHS also should become 0. So how much is the total charge enclosed? How many charges we are having? 3 charges. Where are the charges present? The charges are present on spherical shells. Okay, they are present on spherical shells. Here you have to remember what is the radius of the charge. A sphere. The surface area of a sphere formula you have to remember. So that becomes equal to how much? On the RHS we are having, this is nothing but integration of basically rho s ds on all the 3 shells. Okay, on all the 3 shells, on the shell number 1 plus integration of rho s ds on the shell number 2 plus integration of rho s ds on the shell number 3. Luckily here rho s1, rho s2, rho s3, all the 3 guys are constant values. Okay, constant values. So because of that, if you simply take that out, integration of ds becomes surface area. What is the surface area of a spherical shell? It is nothing but 4 pi times radius square. So this 0 becomes equal to, right now, this 0 becomes equal to, the inner guy has charge density of 20 nano. So 20, nano, let's assume by default. Okay, so into 4 pi radius square. What is the radius of this guy? Smaller shell? 2. So 4 pi times 2 square plus the second one. The second one is -4. Nano is by default assumed. So -4, okay, into 4 pi radius square. Radius is nothing but 4 itself. So this is into 4 pi times 4 square plus the last term. Okay, the last shell, if you notice, this shell has a charge density of unknown value rho s. So this is nothing but rho s into, how much is the radius of that shell? 8. So 4 pi 8 square. So this is 4 pi 8 square. Okay. Yeah. So this is rho s unknown value into 4 pi. Still same problem. Okay. So this is what you have. Okay, this is the last term here. Okay. So again, since the other side is nothing but 0, no, I can do the cancellations. 4 pi is gone here, 4 pi is gone here, 4 pi is gone. So overall, when you do the calculations, what do we get? This is 4 square into minus 4, which is minus 64. This is 20 into 4, 80. 80 minus 64 is nothing but 16, and 16 goes to the other side. So we'll have rho s value being equal to minus 16 by 64. Okay, I think minus 0.25 if you do the calculation. Okay, yeah, minus 0.25, yes. So after you do the calculation here, in this case, you get the answer as nothing but minus 0.25. Okay, so after the calculation, you get the value of rho s to be minus 0.25. Okay, what is units? Units is nothing but nanocoulombs per meter square. Okay, nanocoulombs per meter square, and yeah, that is the final answer here in this question. Okay, yeah, there is a question why Gauss law is called as Maxwell's law. It's not basically called as Maxwell's law; it's Maxwell's equation we call. Maxwell's equations are a basically set of one set of 4 equations, which basically describes the divergence and curl of both electric and magnetic fields, which are required basically to define the electric and magnetic fields. Okay, so without which we cannot mathematically describe the electric as well as magnetic fields, because to describe any vector field, divergence as well as curl of that particular vector field has to be defined. Okay, and these equations were incomplete until Maxwell did some contribution. Okay, so hence all the equations were called as Maxwell's equations, but as such, in this law that we have taken, the Gauss law, there is no contribution of Maxwell. Maxwell has only one single contribution, which comes in displacement current density. Okay, apart from that, there is no other contribution of Maxwell, but still we call all these equations as nothing but Maxwell's equations, because he completed the last piece of the puzzle. So you can assume ki Maxwell is the person who submitted the project. Okay, so maybe some 3-4 people did the project, but ultimately one person submitted the project. Okay, more credit goes to that particular person. Okay, so here also in case of so-called Maxwell's equations, we have Ampere's law, we have Gauss law, we have Faraday's law, we have Lenz's law. We have many people contributing to those set of equations, but ultimately the last piece of puzzle was completed by Maxwell by getting the so-called displacement current density, and hence the entire set of equations were called as now Maxwell's equations. Okay, yeah. So let's move on. So this is one kind of a question that you can get, okay, in GATE exam, which can be answered very well within the time frame. Okay, so all you have to do is nothing but calculate the total charge on each of the shells, add them to the required value. Here anyway this flux density is nothing but 0, means flux also becomes 0. So flux coming out of this 10 meter surface is nothing but 0, means inside this 10 meter surface total charge is nothing but 0. Total charge is present in 3 areas on a shell of radius 2, 4 and 8. These are the 3 areas, corresponding charge densities are given. When you draw this diagram, the question makes much more sense for you, and it becomes very easy for you to answer also. Okay, yeah, let's go to the next question now. A metallic sphere with 1 meter radius, okay, with 1 meter radius. So there is a metallic sphere of radius 1 meter has a charge density of 10 coulombs per meter square. So this guy has 10 coulombs per meter square amount of charge density, and it is enclosed in a cube. So this is now present inside another box. So that is basically a cube. So let's assume this is the cube. This is the cube, okay, of side 10 meters. Of side 10 meters. Maybe this width is nothing but 10 meters. So means a big box which is enclosing this entire, spherical conductor or metal sphere is what you can say. So this cube now I can say encloses the metal sphere entirely. Okay, the metal sphere is entirely enclosed by the cube. So now what you are supposed to say, the outward electric displacement normal to the surface of the cube. Normal, tangential, nothing of that sort is required for us. The outward electric displacement. Look at the units. All the units are in terms of coulombs. So means what? Okay, they are asking us basically total electric flux coming out of the cube. So now again by applying Gauss law, okay, flux out of cube, which is basically a closed surface, is equal to charge inside the cube. So this is simply equal to the charge inside the cube, right? That's it. So by means of what? Obviously by means of Gauss law. Who says this? This now is basically Gauss law. According to Gauss law, flux coming out of the cube also becomes equal to the charge inside the cube. Now inside the cube, charge is present where? Charge is present on the surface of a particular metal sphere. Okay, so that's what they said. Metal sphere is there with surface charge density. So means what? Charges are distributed on the surface of this particular shell with what charge density? With a charge density of 10 coulombs per meter square. And hence what is RHS? RHS is nothing but rho s into surface area. Okay, whose surface area? Surface area of the shell or metal sphere. Of the metal sphere. Okay, which becomes equal to how much is charge density? It is nothing but some 10 coulombs per meter square. Okay, into how much is the surface area of the metal sphere? The radius of the metal sphere is nothing but 1 meter. So this is 4 pi 1 square. So this is 4 pi into the radius of the metal shell square. So what is the answer now? This is 40 pi. Okay. So nowhere in the question you see Gauss law word, but rather, yeah, to solve this question you have to use Gauss law. So understand the Gauss law properly well. It is one of the very, very important topics from not just from GATE point of view, but rather from other exams point of view also. Okay. Yeah. Yeah, good. Let's go to the next question. This is another good question. Very commonly asked question in IES mainly. We never got this model in GATE. We got this question in state exams, BARC, ISRO, all exams except GATE till now. But yeah, there is a possibility that this question may be asked for you. So here 3 charges are given to you and you are supposed to tell how much is the total electric flux coming out of the sphere of radius 0.5 meters. If nothing is mentioned, we assume that this sphere is centered at origin. Okay, so by default, this is by default centered at origin. Okay, so and let me call this sphere as nothing but S. It's the surface, I'm calling that surface as nothing but S. So again, you are supposed to calculate what? The total electric flux phi E out of S. So how much is the flux coming out of S? So that becomes equal to the charge enclosed by S. So all you are supposed to find out is nothing but amongst the 3 charges you are having, which of these 3 charges are inside the surface and which charges are outside. And I only bother about here what charges which are inside the surface, not outside the surface. Okay. So yeah, I am taking this sphere now. So this sphere of radius, how much? 3.5. So 3.5 is taken and I am calling this as nothing but S. Okay. So if you look at the location of this particular first charge is present where? 0, 0. So at what distance this 0, 0 is present from origin, because the center of the sphere is at origin. Okay. So Q1. So we will do 3 calculations right now. In exam also you have to do these 3 calculations. First is nothing but Q1 is located square root of 0 square plus 0 square, which is nothing but 0 meters from the center of the sphere. Okay, from the center of the sphere. So this 0, don't you think it's less than 3.5? Yes, less than 3.5. Means what? Definitely the charge Q1 is present inside only, somewhere inside, maybe at the center only. So this is the location of finally the charge, I can say Q1. What about Q2? What about Q2 now? Q2 is located at what distance from the center of the sphere? Located at a distance of square root of 3 square plus 0 square. So 3 square plus 0 square, which is nothing but 3 meters. 3 meters from again the center of the sphere. Again 3 meters. 3 meters, is it not less than 3.5? Yes. So means what? Definitely even Q2, I don't know where it lies. You know, randomly I can place Q2. I can say this is the position of Q2. Randomly I'm placing. Okay, don't say sir x-axis, y-axis, nothing of that sort. Yeah, it is inside this particular sphere, that's it. What is the exact location? Not my concern. Okay. The last one, Q3. Q3 is located at a distance of square root of, if you see the point there for Q3, 0 square plus 4 square, which is nothing but 4 meters from the center of the sphere. From the center of the sphere. Okay. So this 3.5 right now. Okay. So this, this 4, is it not greater than 3.5? Okay. Now this is greater than 3.5 means what? This is basically outside the sphere. So yeah, randomly I'm placing Q3 now. I simply know that okay, this guy is outside the sphere. So now again apply Gauss law. Okay, if you apply Gauss law, who are inside the surfaces? There are only two charges which are inside the surfaces, which is Q1 and Q2. So yeah, this now becomes equal to Q1 plus Q2. The entire analysis we have done is only for that, to identify which charges are inside the surface and which charges are outside the surface. So this becomes equal to Q1 plus Q2, okay, which becomes equal to the first and second charges. If you notice, this is 5, this is 4, both are micro only. So 5 plus 4 is nothing but 5 microcoulomb plus 4 microcoulomb, and finally the answer is 9 microcoulomb. Okay, so that is the correct answer. Answer is nothing but B. Okay, like I've told, the main goal of this problem is to identify which charge is present inside the surface and which charge is present outside the surface. And if you can do that, yeah, now again by applying Gauss law, you can simply find out, you can find out the total flux crossing the given surface by adding up all the charges which are inside the given surface. Okay. Yes, 9. Good, good. Again, just to let's not deviate from the main discussion here. Pay commissions will happen in their own time frame. Okay, the pay commission is already due for a long time. Okay, it was supposed to be implemented by 2021, so pay commission is already due. So don't bother about the pay commissions. Let's focus on the exam right now. Yeah. Again, now in this question, if you see electric flux density is given. Okay, and if you are confused, you can always look at the units, coulombs per meter square. So D bar is given to you, and you are supposed to find out the total charge inside a cube. Okay, so what was given to you? What was given to you is nothing but D bar, and what was asked for you? The total electric flux. And how do you find out the total electric flux? Yeah, total electric flux becomes equal to now, this becomes equal to integration of rho v dv. Okay, rho v dv. Okay, nice logic. But do I have the information of rho v? No, I don't have the information of rho v. Can I find out the value of rho v from D bar? Yes. By using Gauss law or Maxwell's first equation, okay, we can find out rho v by simply taking divergence of D bar. So del dot D becomes equal to rho v, and yeah, finally from that you get phi E becomes equal to integration of rho v dv. So you are getting charge density from flux density, and by using charge density we are finding out the total charge or total flux coming out of a closed surface. In fact, I'm sorry, total charge. They are total charge, not total flux also. But anyway, both are same only because of Gauss law. Okay. So this now total charge becomes equal to rho v dv only. Okay. We have been given a cube. limits of x, y, z are basically from -1 to +1. Okay, so but first of all we are supposed to get rho v. Let me get the expression for rho v. Okay, what is the formula for rho v? Here you can see from Gauss law, we can say rho v is equal to del dot d. Okay, the given function is in terms of rectangular coordinate system, so I have to take the divergence expression in terms of rectangular coordinate system, which is dou dx by dou x plus dou dy by dou y plus dou dz by dou z. So you have to differentiate x term with respect to x. X term is nothing but x cube differentiation of, differentiation of x cube with respect to x is nothing but, so this is 3x square plus the second one is basically x square y, and when you differentiate the z component with respect to z, there is no z term there, so obviously even the last one becomes equal to 0, and finally this guy becomes equal to simply 3x square. So I got rho v. So then I have to calculate the total charge. What is the total charge right now? Integration of rho v. Now that rho v is nothing but 3x square. So 3x square and dv. What is dv in case of rectangular coordinate system? Dx, dy, dz. So this simply becomes equal to dx, dy, dz. Okay, so this is independent integration of three quantities. First we have 3x square dx, which is x cube, because we get x cube by 3 gone. So x cube is the first term, and then integration of dy is nothing but y, integration of dz is z. X limits are from where to where? -1 to 1, y limits also -1 to 1, z limits also -1 to 1. So 1 cube is 1, -1 cube is nothing but -1. So we'll get 2 here, 2 into 2 into 2, all three guys are nothing but 2's only. Answer is simply 8. Okay, 8. Again, to solve this question, we are making use of obviously Gauss law, right? Yeah, let us proceed. Yes. Solve this question right now. Dou by dou theta of something. What is that something? This is nothing but h1, h3, which is nothing but r sine theta times this guy, which is 100 cos 2 theta. This is basically 100 cos 2 theta divided by r. Okay, so this is the, if you notice, coefficient of theta cap is what? Is it not d theta? Yes. So only d theta remains, remaining terms are 0, and hence this one, if you notice, I didn't even write it. No point in writing the formula also here, because anyway that goes to 0. Even the phi terms are not there, so dou by dou phi of the last part again becomes equal to 0. Okay, so here also it is nothing but 0. Okay, so when you perform this differentiation, what do we get? Yeah, so r and r both are cancelled out, so both r terms are gone. So we have 100 taken outside. We have 100 taken outside right now. So this is 100 divided by r square times sine theta into, see, basically you can write cos 2 theta as nothing but, in terms of sine, we can write this cos 2 theta as this, I believe, to sine, I think, what is sine theta? I think sine theta is nothing but 2 sine square theta minus 1, if I am not wrong. Cos theta, yeah, 1 minus cos 2 theta. Yeah, if I'm not wrong, sine theta is nothing but 1 minus or 1 plus. Sine 2 theta is clear. Expand this cos 2 theta term basically here. we got the answer already. Cos 2 theta. Is it 1 plus or 1 minus? If I'm not wrong, I think it is 1 minus cos 2 theta by 2. Okay, please correct me if I'm wrong. So I'm assuming that sin theta becomes equal to square root of 1 minus cos 2 theta divided by 2. Okay, please tell me if it is correct. I'm assuming it is correct. Square root of 1 minus cos 2 theta by 2. Yeah, correct only. Okay, so we can proceed further. Yeah. So this is what you can take now on the basis of this. What is cos 2 theta? What is cos 2 theta? Cos 2 theta is nothing but this becomes equal to now 1 minus, this becomes equal to 1 minus 2 sine square theta. Okay, so is what I can take here. Cos 2 theta becomes equal to 1 minus 2 sine square theta. Okay. Yeah. So when you now differentiate, you get the expression as total. First multiply them. When you multiply them, you get sine theta minus 2 sine cube theta. What is the differentiation of sine theta with respect to theta? This becomes equal to cos theta, first one. Second one, what is the differentiation of 2 sine cube theta? So 2 sine cube theta becomes equal to 6 sine square theta. Again, differentiation of sine theta with respect to theta is nothing but cos theta. So finally, this is the expression you get. This is the expression for rho v. Okay, so we are done with the expression for rho v here. And once you get the expression for rho v, now we can use this rho v expression to get the expression for total charge. Okay. Yeah. Next, what is the total charge? Q enclosed becomes equal to, this is integration of rho v dv. Again, you got the rho v expression already. Rho v expression here becomes equal to this big I, which is 100 divided by, this is 100 divided by r square sine theta into cos theta minus 6 minus 6 sine square theta cos theta dv. What is dv in case of spherical coordinate system? This is nothing but r square sine theta dr d theta d phi. Okay, you can do a few cancellations. R square sine theta in the denominator, numerator both are gone, and now this becomes equal to 100. I can take it outside. Then we have integration of, first of all, cos theta. What is the integration of cos theta? This is sine theta. Okay, sine theta, and the limits of theta is from where to where? 0 to pi. Okay, and the remaining terms are what? Integration of dr is nothing but r. Integration of d phi is phi. Okay, were you given the r limits? I think you were given r limits, and okay, theta limits are different. R is from 1 to 2, theta is from 0 to pi by 2. Okay, 0 to pi by 2, r is from 0 to 1. Nothing is mentioned about phi. So means what is the limits of phi? Limits of phi is from 0 to 2 pi. Okay, so this is the first one. The second integration is nothing but minus 100. This 100 will go to the second part of the problem also, into 6 into integration of, first one I am separating it out, sine square theta cos theta d theta. This is one separate integration. Integration of dr becomes equal to r. Integration of d phi becomes equal to phi. Limits of phi 0 to 2 pi, r 0 to 1. Okay, so this integration, the limits of the integration is from where to where? 0 to pi by 2. Okay, you can transform this integration now by substituting probably sine theta as nothing but t. Okay, so I am taking here in this part only sine theta becomes equal to t, means cos theta d theta becomes equal to dt, and furthermore on the basis of the limits and the substitution you have taken, theta equal to 0. Theta equal to 0 means t is also equal to 0, the lower limit, upper limit. Theta is 90. Theta is 90 means t becomes equal to 1. Okay. So finally, what will be the answer that you will have for the first part? First part, this becomes equal to See, this is entirely 1. Sine pi by 2 is nothing but 1 minus 0 is nothing but 0. This is 1. This is 2 pi. So overall, all the three terms combined, we have 2 pi into 100, 200 pi. Okay, so the first term is nothing but 200 pi. Okay, what about the second term? First one is 200 pi. Minus, what is the second term? Second term we are having first of all 600 minus 600. Okay. Then what is this integration? The rest all things you have got. Into 2 pi also you have got. So into 2 pi you have got already. The only thing that is missing here is nothing but this integration. So this integration now can be written as, integration of sine square theta is nothing but t square, cos theta d theta is nothing but dt, and the integration happens from where to where? T equal to 0 to t equal to 1, 0 to 1. So means this becomes equal to t cube by 3, and after the limits substitution we get the answer as nothing but 1 by 3. Okay, means the last part of the integration now becomes 1 by 3. So 3 cancels out 600, 200 pi times. So 200 pi into 2 pi is nothing but 400, sorry, only 600, I'm sorry, only 600. Pi should not be there here because pi we have taken separately. Okay, yeah, it cancels out 200 times, 200 into 2 pi we are having, which is 400 pi. So 200 pi minus 400 pi becomes equal to, what is the final answer now? Minus 200 pi. Okay, so this is a final answer. Okay, the problem as such is very simple from EMF point of view. If you see, what is the EMF part? This is one EMF part. Okay, and the other EMF part is nothing but another EMF formula is this part. That's it. So EMF ends there. Rest all things whatever you are doing is nothing but basic integrations, basic calculus, nothing great. So understand EMF part of EMF problems, like I always say in the classes also, they are very simple, only 10%, 20%. The remaining portion of the problem is mainly vector calculus as well as calculus. Okay, so that is the part you have to be very strong in, right? Yeah, let's go to the next question. Now this is a previous question, a recent question of GATE, in fact 2021. So we have been given a vector field in terms of cylindrical coordinate system. So this symbol is phi for us, understand? So, and here also d bar has only two components. D bar is given to us. Okay, so what is this guy? This is d rho, and what is this guy? This is d phi. This is d phi, and yeah, a rho, a phi, a z are unit vectors, we know that. So then you are supposed to find out net flux leaving the closed surface of the cylinder. So this is the dimensions of the cylinder given to you, and close to some 2 decimal places is dash. So total flux, what is the formula for total flux? Phi E becomes equal to, this is integration of d bar dot ds bar. Okay, so since it is given as closed surface, I am taking this as nothing but closed surface integration. But how do you perform closed surface integration? By applying divergence theorem. Okay, so by applying divergence theorem, so this becomes equal to integration of del dot d dv. So yeah, the question involves now calculating divergence of d bar. So let us calculate divergence of d bar. So del dot d. The given vector field is in terms of cylindrical coordinate system. So in cylindrical coordinate system, what is the expression of divergence? What is the expression of divergence? 1 by rho, okay, dou by dou rho, first one, of h2 h3 times d rho. So this is nothing but rho times d rho plus dou by dou phi of d phi. The last one is nothing but dou by dou z of rho times dz. Okay, so in the given data, if you notice, in the given data, yeah, we have d rho is given, but dz is nothing but 0. So I don't even have to consider this dz. D rho is given as how much? This is some rho cos square phi. So this is rho cos square phi. And what is d phi? D phi is z square sine square phi. Okay, so let us do the calculation now. So this becomes equal to 1 by rho You are differentiating with respect to rho what term? Rho here, rho square. So differentiation of rho square with respect to rho becomes how much? 2 rho. Okay, 2 rho. Into anyway you are having cos square phi, no? So into cos square phi. Okay, plus here you are differentiating with respect to phi. Z is a constant, so Z can be taken outside. Z square. And differentiation of sine square phi with respect to phi becomes how much? That is nothing but 2 sine phi cos phi. So this is 2 sine phi cos phi. Okay. So this is the expression of divergence now. So this is done. So this is a del dot D. Okay. Substitute this value here. When you do that, this becomes equal to now. This is integration of two terms. The first term is 1 by rho. Okay. 1 by rho. This is 2 rho cos square phi plus Z square. So 2 sin phi cos phi, we can write this term as nothing but 2 sin phi cos phi as sin 2 phi, right? Yeah, this becomes equal to sin 2 phi. So I'll write that same thing here. Okay, so this is now sin 2 phi. Now, what is dV in case of a cylindrical coordinate system? dV is rho, d rho, d phi, dz. Okay, so because of this, I can cancel out the rho here as well as rho on the outside. So now I have to perform two integrations. Two integrations, both are volume integrations. The first one is what? Integration of 2 I can take it outside. Integration of rho d rho is rho square by 2. Okay. Cos square phi. How do you take cos square phi? Cos square phi becomes equal to, okay, this guy becomes equal to 1 plus cos 2 phi by 2, right? Yes. So this is what is cos square phi. I am writing everything in terms of only, I don't want to integrate cos square phi directly, it becomes a tedious process. So I am converting it like that. What is the integration of 1 by 2 d phi? So that becomes equal to phi by 2 plus. What is the integration of cos 2 phi? Integration of cos 2 phi is nothing but sin 2 phi divided by 2. Already you are having by 2. So this becomes equal to sin 2 phi divided by 4 now. Limits of phi will be from where to where? 0 to 2 pi. Okay. And lastly, integration of, there is no z term here, so 1 dz. Integration of 1 dz is nothing but z. Okay. Substitute the limits. Limits for rho. They said 3 means the starting point is implied. That is, starting point for rho is what? Rho starts from always 0. So this is from 0 to 3. And z is changing from 0 to 2. And phi limits anyway are implied, assumed. That is the first part of the integration. Second part of the integration, we have 1 d rho. There is no rho term, means 1 d rho means integration of 1 d rho is rho. Limits changing from 0 to 3. And we have integration of sin 2 phi. What is integration of sin 2 phi? Minus cos 2 phi divided by 2. Limits 0 to 2 pi. Okay. And lastly, integration of z square. Integration of z square is nothing but this is z cube by 3. Limits of z is from 0 to 2. Okay. But if you notice, if I substitute these limits, it looks like a lengthy expression, but there is a cancellation also. Half of the terms are getting cancelled out. For example, this term, after you substitute the limits, what do we get? Sin 4 pi 0, lower limit sin 0 also is nothing but 0. So only this part is going to 0. So this part is going to 0 after the substitution of limits. Similarly, here if you notice, what is cos 2 into 2 pi? Cos 4 pi 1, cos 0, lower limit also becomes how much? 1 only. So hence this entire term becomes equal to 0. So due to which the second term entirely goes to 0, but not the first term. In the first term still this phi by 2 remains, because upper limit is 2 pi, lower limit is nothing but 0. So due to which this bracket term becomes equal to 2 pi minus 0 by 2, 2 pi by 2, which is nothing but pi. Okay. Whereas this first bracket term becomes equal to, this is 3. 3 square means 9 by 2. Okay, you'll have 9 by 2 here. So this is 9 by 2. And the last one is simply equal to 2. Okay. So when you multiply everything, what do we get? 9 by 2 into 2 is nothing but 9. 9 pi into 2, 18 pi. So the answer in this case becomes equal to 18 pi. Okay. Yeah, multiply 18 with pi, you can use virtual calculator for that and get the answer. it's not a big deal. Okay, but yeah, look at this. This is the previous GATE question, pretty recent one, that too, EC paper 2021. All you have to do is nothing but be patient and do the calculation. EMF portion here is what? Only one single formula I should say, that is nothing but flux is equal to flux density into area. But apply divergence theorem. When you apply divergence theorem, this is what you get. But to solve this question, you have to remember divergence in case of cylindrical coordinate system, dV also in terms of cylindrical coordinate system. Only then you can proceed further in this question. But as such, formula based, this is not a great question. Very simple question, straightforward question. Okay, and this is a repeated model also basically. Let us go to the next question now. Yeah, good minus V. Again, same kind of a model. Here, again you have the data given in terms of cylindrical coordinate system, but examiner is using the notation of R. Okay, whatever is R according to examiner is for us rho. So while writing the data, you always write in terms of your comfortable format. Okay, and so given d bar, you have been given d bar expression in terms of coulombs per meter square. Then the total electric flux, you are supposed to calculate, emanating from a volume enclosed by a solid cylinder of radius 3 meters. So the radius of the cylinder is nothing but 3 and height of 5 meters. Okay, height of 5 meters oriented along z axis with the base at origin, extra description. Okay, extra description. So means z limits according to the last part. What is the data we have? Z is changing from where to where? 0 to 5. Okay, these are the limits of Z. And furthermore, from this, what is the limits of rho? Rho limits is from 0 to basically 3. Okay, rho is basically changing from 0 to 3. So these limits are not directly given to you. If you notice, they have been indirectly given to you. And phi limits we all know is by default always fixed, which is nothing but 0 to 2 pi. Okay, so let me write d bar right now in terms of our notation, our comfortable notation, which is d bar becomes equal to, this is 15 times a rho means rho cap plus 2r means 2 rho phi cap, and lastly we have minus 3rz means 3 rho z cap. Okay, so the coefficient of rho cap is nothing but d rho here. So this guy is d rho, and coefficient of phi cap is d phi, and coefficient of z cap becomes equal to dz. Okay, so this is the given function, given vector field. So like in the previous case, what we are supposed to calculate now also, total flux. Okay, total electric flux becomes how much? This is nothing but integration of d bar dot ds bar through the closed surface S, which by applying the divergence theorem, when you apply divergence theorem, okay, so this can be written as integration of del dot d dv over the volume. For the volume, we know the limits. Rho limits are 0 to 3, z limits 0 to 5, phi limits are from 0 to 2 pi. Okay, so next we have to calculate first of all del dot d for the given function. So let us calculate del dot d. The given function is in terms of what coordinate system? Cylindrical coordinate system. In cylindrical coordinate system, what is the formula? 1 by h1, h2, h3, 1 by rho, dou by dou rho, okay, of h2, h3, which is nothing but rho times d rho, plus dou by dou phi of h1, h3, both are 1, times d phi, plus lastly dou by dou z of h1, h2, which is basically rho times dz. Okay, so in this given function, what is the value of d rho? D rho is nothing but 15. So this part is 15. What is d phi equal to? D phi is equal to 2 rho. So this is 2 rho, and z is minus 3 rho z. So this part basically is minus 3 rho z. Okay, yeah, after the substitution, what will be the answer? See, usually some people will take this 1 by rho inside. Don't do it, because afterwards you are having anyway dv multiplication, no? So you are multiplying that, where is that? You are multiplying this del dot d with respect to dv, and here in dv what do we have? Rho d phi dz, right? So anyway that rho is there, that rho that you have here and the rho in dV as well as the rho that you have got here, both will be cancelled out. So don't take this 1 by rho inside, at least in terms of calculation, keep it outside only. So this is 1 by rho, okay. First one, a differentiation of rho with respect to rho is how much? 1, so we will have 15 only, first one. Second one, there is no phi term, so hence 0. The last one, minus 3 rho z, differentiation with respect to z becomes equal to minus 3 rho into rho becomes equal to minus 3 rho square. So overall this is minus 3 rho square. So this becomes equal to finally 15 minus 3 rho square divided by rho. So don't take this rho, multiplication, don't write it as nothing but 3 rho square by rho is nothing but 3 rho, waste of one step, okay. So finally what is the flux? Flux becomes equal to integration of del dot d, which is 15 minus 3 rho square by rho times dv. What is dv in case of cylindrical coordinate system? Rho d phi dz, okay. So rho as well as rho is gone. This becomes equal to now 15. I can take it out, okay. Now the first one is integration of d rho d phi dz because there is no term in the 15. So 15 into rho phi z, because integration of d rho is rho, d phi is phi, dz is nothing but z. Rho limits 0 to 3, phi limits 0 to 2 pi, z limits 0 to 5. Okay, so this is the first part. What about the second part? The second part is rho square integration is basically rho cube by 3. Okay, rho cube by 3. And then in the second part we have d phi integration phi, dz integration z. Okay, z limits 0 5, phi limits 0 2 pi, rho limits 0 3. Okay, yeah, 3 and 3 is gone. Okay, so finally what is the answer now? 3 here, 2 pi, 6 pi into 5, 6 pi into 5 is 30, 15 into 30 is, if I am not wrong, 450, right? So 10, 10, 45, yeah, 450 pi. This is 450 pi minus what is the second term? 5 into 2 pi, 10, and this is 27 minus 270, okay, minus 270 pi. 450 minus 270 pi becomes how much? This is 180 pi. Okay, so this is MCQ question, 180 pi. Do we have that as option? Yes. Okay, simple question, same procedure as compared to the previous case, nothing great, right? Yeah, next question I want you guys to solve it. Yeah, this is again pretty recent question, 2020 electrical paper. If you see, this question more or less comes every year. This kind of a model, either in electrical or EC. Most of you, I believe, are writing in both papers. 2020 we have this question, 2021 we had this question. Okay, again 2020 electrical paper, similar question we are having. And yeah, again 2022 EC paper, again the same kind of a question. Okay, so in all these years, more or less every year you will have this one question for sure. Okay, and more so 2024 and 2023 we didn't have this kind of a question, at least Gauss law kind of a question. So this is a question waiting to be asked. So these are the questions you are not supposed to miss basically while practicing. Okay, Manasvi, I think you have done some mistake. It should be 180. Okay, 180 pi. Okay, now you guys try out this question. I'm sorry, not this one, some other one. Yeah, this question. Again, while writing the data, try to always write this in your comfortable notation. Okay, so cylindrical coordinate system means what? We use the notation of rho phi z. So I can write this E bar to be equal to how much? This is 2 rho cap plus 3 by rho phi cap. Lastly, we have 6 z cap. This is 6 z cap, and the coefficient of rho cap is nothing but E rho. Coefficient of phi cap is E phi, and coefficient of z cap is Ez. Okay, and furthermore, this is nothing but electric field intensity. So this is the electric field intensity E bar. Okay, E bar term, not D bar. And what you are supposed to calculate, if the above field, then the volume charge density. Okay, you are directly supposed to tell only volume charge density. What is the volume charge density? So we don't even have to perform the integration. Much simpler question this is. Then what is the expression for volume charge density? Volume charge density rho v becomes equal to del dot d, right? But I don't have the information of d, I have the information of E. So then I can write this as nothing but this is del dot epsilon times E bar. Okay, epsilon, what is the value of epsilon? Epsilon formula is nothing but this is epsilon naught times epsilon r. Now all options are in terms of epsilon naught only, but epsilon r is given to us. Epsilon r is given as 2.25. Okay, so I can take that 2.25 epsilon naught outside. So this becomes equal to 2.25 epsilon naught del bar dot E bar. Ultimately, again, to solve this question, you have to get del dot E. So let's solve del dot E for the given case. Again, the given vector field is in terms of cylindrical coordinate system. In cylindrical coordinate system, what is the formula for divergence? 1 by rho, dou by dou rho, rho times E rho, dou by dou phi, E phi. By now you should have got comfortable with this formula, dou by dou z, rho times Ez. Okay, and this becomes equal to 1 by rho, E rho. What is the value of E rho? E rho is 2 rho. So this value is 2 rho. And what is E phi? E phi I believe is 3 by rho. So this is 3 by rho. And lastly, what is Ez is nothing but constant value 6. This is a constant value 6. Okay, so whenever you perform now differentiation, very simple result right now. Expressions, first expression look bigger, but rather the second answer, the second step is simple step only. So 2 rho into rho is 2 rho square. So differentiation of 2 rho square becomes 4 rho. The first guy is nothing but 4 rho plus there is no phi term, there is no z term. So both are zeros. 4 rho by rho becomes equal to now 4, simply 4. Okay, which is what you are supposed to substitute in the previous expression. So finally, what is rho v? Rho v we have got 2.25 epsilon naught times del dot E. What is the value of del dot E in the given case? This is nothing but 4. So rho v becomes equal to 9 times epsilon naught. Okay, 9 times epsilon naught. See, the options are given to you in such a way that let's assume that you miss this 2.25. If you don't take this 2.25, so then the answer you would have got is nothing but 4 epsilon naught. Is also one of the options if you notice. But anyway, in this case, the correct answer is nothing but 9 epsilon naught. All these questions that you are seeing, the previous one, this question and this question, all these questions are 2-mark questions only that were asked in GATE exam. Okay, including in fact even this question also, the new question, even this is also a 2-mark question. Okay, please calculate this now. Yeah, good. Please solve this question. Again, what was given? D bar is given in terms of coulombs per meter square flux density, and what you are supposed to calculate? Total electric charge enclosed, okay, within the R. And what is R? R is nothing but a cubical region. Cubical region means what? Is it not a closed region? Yes, cubical region is a closed region. So you are supposed to calculate the electric charge inside. So Q inside R becomes how much? Integration of rho v dv. Do I have the information of rho v? No, I don't have. But can I calculate? Yes, I can very well calculate. What is the value of rho v now? So this rho v now becomes equal to del dot d. See, the moment you are able to write these two formulae, notice, please notice that your EMF portion is complete. Okay, so there is nothing else in EMF portion that is required to answer this question. Okay, so this is what is EMF portion for you. Rest all is basically calculus only. Okay. So a nice thing is nothing but I have the data in terms of rectangular coordinate system. So what is divergence expression in case of rectangular coordinate system? Del dot d becomes how much? Del dot d is dou dx by dou x, differentiate dy with respect to y, differentiate dz with respect to z. and this becomes equal to, when you differentiate the x component with respect to x, we get this as 3x square, and y with respect to y, y cube differentiation with respect to y is 3y square, and xy square with respect to z, there is no z terms there, hence 0. So all you have is nothing but this is 3x square plus 3y square. This is what now you are supposed to integrate. So finally, what is q inside? Q inside r becomes equal to, this is integration of rho v dv, which becomes equal to integration of 3x square plus 3y square dx dy dz, which becomes equal to, what about the first one? Integration of 3x square is x cube by 3 into 3, which becomes equal to simply x cube. Integration of dy is y, integration of dz is z, and the second one is, there is no x terms, so integration with respect to 1 dx is nothing but x, integration of 3y square is y cube, integration of dz is z. Substitute the limits here. For all three cases, x, y, z, the limits are from minus 0.5 to plus 0.5. Every guy, both all x, y, z, all are from minus 0.5 to plus 0.5. So yeah, I think there's a 0.5 to 0.5. Same with all cases. Okay. So when you do the calculation here, what do we get? This becomes equal to how much right now? 0.5 means 1 by 2. So 1 by 2 whole cube becomes equal to 1 by 8, minus of minus again, minus 1 by 2 whole cube becomes equal to minus 1 by 8. So 1 by 8 minus of minus 1 by 8 is nothing but 1 by 4. So this is 1 by 4, and this guy, upper limit is 0.5, lower limit is minus 0.5, 0.5 minus of minus 0.5 is nothing but 1, so 1 and 1. So finally you are getting this as nothing but 1 by 4 into 1 into 1 plus 1 into 1 by 4 into 1, which is basically first one 1 by 4, second one 1 by 4. Total you are having 1 by 2, 0.5. Okay, so the overall answer is nothing but, rounded off to 2 decimal places, it is nothing but 0.5. Okay. So this is the answer. 0.25, please Manasvi verify. Should be 0.5. There are two terms, right? Yeah. Okay. So these are the silly mistakes you have to avoid. Calculus mistakes. See, if at all you are going wrong in this kind of problems, nowhere you will go wrong here. EMF part of EMF problems are very simple. This portion, which involves basically vector calculus, that is where you have to be careful. Okay. Yeah. We'll go for the next problem. Next concept, in fact. One more application, very important application of Gauss law. A similar kind of a thing you also see in Ampere's law is nothing but how to use Gauss law to find out E bar and D bar expressions for the volume charge distribution scenario, and that was specifically for spherical volume charge distribution scenarios. So here I am taking a generalized scenario, I am taking a non-uniform charge distribution scenario. I am taking this scenario, which is non-uniform spherical charge distribution scenario. So the story goes like this. Here the charge is placed in such a way that 0 to r you are having charges, and what is the value of charge density? Rho v. And I am assuming that rho v is a function of, okay, I'll write it like this. Okay. So whenever I take the inside region corresponds to 0 less than, this is basically 0 less than r less than a. So r less than a means you are inside. Okay, you are inside what? Inside the charge cloud. And inside the charge cloud is what you are having, rho v. And rho v is basically some function of r, or it may be constant also. That's a different story. If it is constant, we call it as uniform spherical charge distribution. If it is a function of r, we call it as non-uniform spherical charge distribution scenario. Okay, so non-uniform distribution is a generalized case, uniform distribution is a special case of non-uniform distribution. Okay, and hence we are discussing only non-uniform charge distribution scenario. And outside means what? In this region, can I say R is greater than A? Yes, we are outside means R is greater than A. So this is basically outside. So outside, how much is the charge you are having? I don't have any charges here. So rho v becomes equal to 0. Okay, doesn't mean that on the outside there is no electric flux. There is still electric flux because of enclosed charges. Okay, at this point you need not have charges to produce electric field intensity. Okay, imagine that this is sun. Sun is producing some radiation. Okay, so if I am taking a point outside sun, don't you think the effect of sun is felt there? Yes, definitely the effect of sun is felt there. There is no sun. Let's assume at the location of Earth there is no sun, right? Yes, but still don't we experience solar radiation? 100% yes. So at the point outside the charge distribution, charge density is 0, but still here there can be electric field intensity. Okay, and how do you find out that electric field intensity? So we have divided this into two parts. One is nothing but inside. Okay, so where you are trying to calculate, okay, inside or outside. Okay, so that depends on whether you want the data for R less than A or R greater than A. So if it is R less than A, yeah, if you notice this, is it not equal to flux only? Is it not equal to flux coming out of S? Yes, even this is also d into 4 pi r square. In case of spherical charge distribution, what is the surface area of a sphere? 4 pi r square. So d flux density into surface area 4 pi r square, which is a total flux, becomes equal to RH is, if you notice, integration of rho v dv. What is integration of rho v dv? Integration of rho v dv is nothing but charge enclosed only. Okay, so in this case, all you have is basically charge enclosed. Either this one or this one, both of them are basically the terms of charge enclosed. But now the important part is limits. What are the limits you are taking? The limits for the inside case, the entire expression is same, d into 4 pi r square, d into 4 pi r square, inside, outside. Here also rho v dv, here also rho v dv. The integration limits, if you notice, here it is from 0 to r, okay, here it is from 0 to a, where a is nothing but radius of the charge cloud. So this is nothing but the radius of the spherical charge. So the spherical charge exists from where to where. So that radius of spherical charge is nothing but the a here. Okay. So this is a small difference, but in both cases, inside outside the formula is same. D into 4 pi r square becomes equal to integration of rho v dv. Like I have told, you will be given some rho v as a function of r, and that rho v as a function of r is what you are supposed to substitute here. But in the first case, for the inside scenario, limits are from 0 to r. Outside scenario, limits are from 0 to a. Okay. And if at all this rho v is uniform, or the charge distribution is uniform scenario, so in that case rho v is not a function of r, rho v is constant. If it is rho v is constant, can I take this outside? Yes, I can take rho v outside only whenever the rho v is constant, happens whenever the charge distribution is uniform. Okay. Yeah. Let us go for the next question now. Simple question. A volume charge density of 20 r. See, this is now a function of r. Some kind of a function of r is given to us, lies within a spherical surface of 1 meter radius. So as per our standard expression, this 1 meter that you see here is nothing but a. This is a. Okay. Find the electric displacement everywhere in the sphere. So in the sphere means what? Inside or outside? Inside. Okay. Inside. So now you are supposed to calculate the expression for electric flux density or displacement density inside the sphere, means r less than a. So for inside scenario, what is the logic for this problem? The logic is nothing but d into 4 pi r square becomes equal to integration of rho v dv. Okay, integration of rho v dv. Rho v expression is given. Rho v is equal to 20 r. So this is equal to 20 r. dv in case of spherical coordinate system is r square sine theta dr d theta t phi. Okay, guys, I am giving you certain data. Do remember those numbers. It will make your calculation simpler. Integration of sine theta d theta For theta from 0 to pi is nothing but the answer is 2 if you do the calculation, and integration of d phi. Integration of d phi for pi from 0 to 2 pi is nothing but 2 pi. And both combined, integration of sine theta d phi becomes equal to 2 into 2 pi, which is nothing but 4 pi, which is what we see here. Sine theta d phi. Okay, this integration becomes equal to now 4 pi. I am doing the calculation directly here. 4 pi. And then yeah, we have 20 into, there we have 4 pi, okay, into r square. R into r square is nothing but r cube. Integration of r cube is how much? R power 4 by 4, okay. The limits are from where to where? 0 to r only. LHS we have d into 4 pi r square, okay. Yeah, now you can do the cancellations. You can do the cancellations right now. So 4 pi here is gone, and 4 cancels out 25 times, and r power 4 here, r square, r power 4 by r square becomes r square on the RHS. So finally the answer now becomes equal to here. So in this case answer D becomes equal to, coefficient is nothing but 5 we have. 5 r power 4 by r square is 5 r square. What is the units now? Units is nothing but coulombs per meter square. What is the direction? Direction is always radial direction, r cap direction, okay. So that's it. So if you remember this starting point, no, all you have done is nothing but apply Gauss law. So if you have known the starting point, a lot of time can be saved in these kind of problems, okay. Yeah. So let us go for the next one. Next question. This is again a previous question, long ago asked, but rather a good question, okay. Only thing is here you are having uniformly charged sphere, okay, of radius how much? R. Radius of the charge cloud is nothing but r. In our language this is basically called as A, okay. So this is basically called as A. Okay. So in the first case, r is equal to capital R by 2. So means, can I say that this is same as r less than A scenario? Yes. And the denominator term, if you notice, this is a scenario of r equal to 2r, means definitely r is greater than A, because small r is nothing but 2r and A is nothing but capital R. Here also same story. Small r is given as r by 2 and A is equal to r reference. Okay. So this is r by 2 and this is r less than here, greater than here. Okay. So we have to find out first of all expression for electric field intensity inside as well as outside, and then take the ratio of both and give the answer. Okay. So first of all, the first analysis is for inside scenario. Inside scenario. Okay. We have to write in terms of E here, but anyway we will write first of all in terms of D. D into 4 pi r square becomes equal to how much? Integration of rho v dv, integration from 0 to small r, and hence this becomes equal to, here rho v is constant. So since you have been given uniform distribution of charge, so rho v is constant. Rho v is equal to some rho naught constant value. Okay, since it is uniform, and because of that I can substitute that constant value here. If rho v is constant and take that constant outside, integration of dv is nothing but what? Volume. Whose volume? Volume of a sphere. Volume of a sphere. What is the volume of a sphere whose radius is nothing but r? This is 4 by 3 pi r cube. Okay, and now you can do the cancellation. 4 pi gone, r square cube is gone. So finally the answer for D, D becomes equal to how much? This is rho naught into r divided by 3, and from this what is the expression for E? E becomes equal to rho naught r divided by 3 epsilon. This is the expression for E inside. Okay, next same kind of a discussion we have to do it for outside. Okay, now outside, Again, what is the logic? D into 4 pi r square becomes equal to integration of rho v dv. Integration happens from 0 to a, and rho v is constant, which is nothing but rho naught, into what is the integration of dv? Volume of a sphere whose radius is a. So this is 4 by 3 pi a cube. Okay, like in the previous case, if you do the cancellations, so 4 pi here is gone. R square cancellations is not possible currently, and due to which the final answer now is, nothing but D becomes equal to, this is rho naught a cube divided by rho naught a cube divided by 3 times r square. So 3 r square, and hence E becomes equal to, now E is equal to rho naught a cube divided by 3 epsilon r square. So these are the expressions for E inside, outside we have got. Now since you are supposed to do this calculation, okay, now let's get back to this calculation. Yeah, what is this? This becomes equal to E. What is the value of R I am supposed to substitute? Capital R by 2. Okay, so this is rho naught capital R by 2 divided by 3 epsilon, numerator value, because inside region you are taking, because R less than A means inside. This is inside. R greater than A means outside. So I am supposed to use the outside expression here. For outside, what is the formula we have? Rho naught a cube. What is the value of A? A is nothing but R. So everything is in terms of R, capital R. So I am writing it as nothing but R cube divided by 3 times epsilon. 3 times epsilon times R square. What is the value of small r? Small r is nothing but 2r. So this is 2r whole square. That's it. Now you can do the cancellations. Rho naught by 3 epsilon, rho naught by 3 epsilon is gone. Numerator is ultimately equal to r by 2 only. Denominator, what do we have? You have to take one more step. So this is r by 2 in the numerator. Denominator we are having r cube divided by 8r square. 8r square. Okay, that's it. So when you do the calculation, finally what do we get? R by 2, r by 8. So r by 2 by r by 8 means, I think this is 4 if I am not wrong. Okay, this becomes equal to 4. Someone please cross verify. 0.5 you got? Oh, square, I'm sorry. This is square, no? Okay, my mistake. 4. It's my silly mistake. 4. So 2 by 4 overall you're having, correct? This is square by 4, I think 2. Okay, 4 by 2, answer is nothing but 2 in this case. My bad. Right? Final answer is nothing but 2. Okay. Again, this requires the application of Gauss law only. What we have done here is, how did you get this expression, by the way? Flux coming out of a closed surface, or in the previous case also. Okay. Here, yeah, flux coming out of a closed surface becomes equal to charge inside that particular closed surface. Okay. But rather, by remembering this, we can save a lot of time in exam. We can directly write this expression and do the calculation. Okay. So we don't even have to think, this is a Gauss law problem, and then probably I'm supposed to write Gauss law as nothing but flux. Flux is written as D into surface area. Nothing of that sort. You can directly start with this step. Okay. It will save a lot of time for you in the exam. Right? Yeah. Yeah. Good, Rohan. Let's proceed. This is another good question. We never got this question in GATE exam though. A similar kind of a question was asked in civil services, IES, mains, okay, many other exams, but rather not in GATE yet. But there is a possibility that this question can be asked in GATE exam also. Okay, so try answering this question. Here, now you are supposed to find out the maximum value of electric field intensity, where the maximum value of electric field intensity occurs. So first you have to get the expression for electric field intensity and then differentiate that particular function and equate that to 0 to get the condition for maxima. Okay. So even for differentiating that, we require the expression for electric field intensity. So the step 1 here is nothing but to get the expression for electric field intensity. So please get that first. Again, if I am taking inside scenario, which is r less than a scenario, what is the logic? D into 4 pi r square becomes equal to integration of rho v dv. For the inside scenario, limits are from where to where? 0 to r. Solve parallelly with me, 0 to r. Okay. And this becomes equal to how much? This is rho v. Let's substitute rho v right now. This is rho v is rho naught into 1 minus r square by a square. Okay. dv. What is dv in case of spherical coordinate system? We have spherical volume charge here. So this becomes equal to r square sine theta dr d theta d phi. Okay. So this sine theta d theta d phi, when you integrate that, finally you will get the answer as nothing but 4 pi. Okay. So now RHS becomes equal to rho naught into 4 pi taken outside. Integration of r square is sent inside. So this is integration of r square dr minus r square into r square is nothing but r power 4 by a square dr. And the limits of integration is from where to where? 0 to r. 0 to r. Okay. So this is now 4 pi rho naught into, please perform this integration. Integration of r square is nothing but r cube by 3 minus integration of r power 4 is r power 5 by 5 a square. Okay. And that becomes equal to LHS d into 4 pi r square. Okay. So I can cancel out the 4 pi terms here everywhere, and then I can get the expression for d. Then I can get the expression for d. I'm writing it here. Now what is the expression for d? D becomes equal to, on the basis of this, rho naught r cube by r square is r by 3 minus r power 5 by r square is nothing but r cube by 5a square. So this is the function for d, and on the basis of this, what is the function for electric field intensity now? This is d divided by epsilon, which becomes equal to rho naught by epsilon r by 3 minus r power 3 divided by 15 times a square. Okay. And I want the condition for Emax. Okay. So for Emax, all we have to do is nothing but we have to differentiate this. What is the variable here? R, and equate that to 0. When you do that, what is the result that you get now? Differentiation of r by 3 is nothing but 1 by 3. 1 by 3 becomes equal to differentiation of r cube is 3r square. So this is 3r square divided by 15 a square. Okay. And equate that to 0. When you do the calculation here, you get the answer as root power 15 divided by 3. Square root of 15 by 3 becomes equal to, or square root of 5 by 3. Okay, it doesn't matter what you take. So this overall becomes equal to, please do this calculation. I think square root of 5, sorry, 5, not 15. Why 5 became 15? It should be 5. Okay. Square root of 5 by 3 becomes equal to, now this is 0.745 times a. Right? That's it. So hence correct answer is nothing but option C. Okay. Yeah, square root of 5 by 3. Okay. And the answer becomes equal to 0.745. See, like I've told, this question, this model also we didn't get, wherein first you have to calculate electric field expression, and from that maybe find out the condition for Emax or find out Emax. So such kind of a problems we never got, and this as such is a very important model also. Okay. One I think 2015 or 14 in IES paper, if you see, this was given as 100. So 100 means what? This becomes equal to obviously 10 square. So A is nothing but 10. So when you substitute that value here, you get 7.45. So that was the answer in that particular paper. Okay. But nevertheless, this model has not yet been asked in GATE exam. If asked, so please be very cautious. This is also basically exercise question of Sadiku. Same question was also asked in, like I've told you, IES exam, civil services mains exam, many other exams except GATE exam. So in GATE also the question can be repeated. Okay. Yeah. Okay. So we will take a small break here, guys. Small break here. We will be back by, it's almost 10 to or 5 to 4. Okay. We'll be back by 4:15. 20-minute small break. We'll take. Okay. Today's session will be a bit longer session. Okay. So today we will take a longer session. We have to complete both electrostatics as well as also the magnetostatics. Both portions important topics. Okay. So we are, still midway only. We have a lot of more content to cover. So we'll be back after by 4:15 p.m. Come sharp by 4:15. The next topic is about the different types of the charge distributions. Again, we have got questions on the basis of this, either directly or indirectly. We have got questions on this. So we'll discuss that. And after this, another important topic, which is potential. Okay. After we cover this topic, we will do a few problems, and then we have the important topic of potentials here. Okay. Very important topic. So we have lot of problems to cover in this particular topic. This is one of the most important topics in, again, electrostatics, which is what we will cover in the next session. Okay. Yeah. Okay. So welcome back. Okay. So welcome back everyone. Yeah. So after this Gauss law, in Gauss law, like I've told you, two important topics are the Maxwell's first equation, which is rho v is equal to del dot d, and one more important formula or one more important concept there is nothing but this guy, that is spherical volume charge distribution. Okay, non-uniform case. So this is one of the very commonly asked questions in the GATE exam. Okay, so let's go for the next topic. The next topic, you have to know the expressions for electric field intensity as well as flux density for some of the common charge distributions. Okay, so in the first case we have point charge placed at origin. So whenever we have point charge placed at origin, so in that case the first one always in this discussion, first one is always E bar expressions, okay, and this one is D bar expressions. Okay, so the expression for electric field intensity is given by Q by 4 pi epsilon r square. In all these formulae, no, you will see 1 by 4 pi epsilon in the denominator. A lot many times you see 1 by 4 pi epsilon. If nothing is mentioned, we can assume free space, and in case of free space, okay, we can take this value of 1 by 4 pi epsilon, okay, wherever it is, 1 by 4 pi epsilon naught. For calculation, you can write it as nothing but always 9 into 10 power 9. Okay, so this is the value of 1 by 4 pi epsilon naught. So yeah, in many of the problems you have to use this 1 by 4 pi epsilon naught, and if nothing is mentioned about the medium, we can assume the medium as either free space or air. Okay, so then this epsilon becomes equal to simply epsilon naught. Okay, so in the first case we have a point charge placed at origin. So whenever we have point charge placed at origin, the charge magnitude is nothing but q, and this point is also nothing but origin. So at some point of interest P, if at all I want to find out what is E bar, so that expression of electric field intensity at point P is given by Q by 4 pi epsilon r square, where r is nothing but distance between the point of interest as well as charge of interest. Direction is always radial direction, okay, r cap. And in the second case, whenever you have point charge not placed at origin, maybe this is the location of charge Q, okay, so this is where you have placed the charge of interest. And like in the previous case, this is a point of interest. Point of interest has a position vector of r bar. So here r bar is nothing but position vector. Understand? This is the position vector of P. Okay, of P, of the point P. And similarly, whatever r1 bar you are having is also basically position vector. This is the position vector of the location where charge is there. Okay, for the location of charge Q. And we know how to calculate position vectors. If let's assume x, y, z is a point of interest. So in that case, if this guy is nothing but x comma, y comma, z. So in that case, position vector is given by x, x cap plus y, y cap plus z, z cap. Okay. And if this point P1 is given by, let's assume some x naught, y naught, z naught. So accordingly, the position vector r1 bar is also given as, this is x naught, x cap plus y naught, y cap plus z naught, z cap. So in these kind of problems, you are supposed to solve it by using this position vector logic. So in that case, what is the expression for electric field intensity? R square is replaced as now r bar minus r1 bar whole cube. Numerator is no more unit vector, but rather that is r bar minus r1 bar. Okay. So this is q by 4 pi epsilon, which is what you have here also, into r bar minus r1 bar divided by r bar minus r1 bar whole cube. Here the r bar is nothing but position vector of point of interest, and r1 bar is nothing but the position vector of charge where the or the location of the charge, where the charge is placed. Okay, and if you don't take that epsilon term, in that case we get the expression for d bar there. Okay, next is nothing but finite length line charge. So we have finite length line charge here. So this is the finite length line charge. Length is finite, not infinite, and having a charge density of rho L coulombs per meter, and at a distance of some rho meters away from, this is basically rho, Okay. So at a distance of some rho meters away from the charge density, okay, what is the value of electric field intensity? The angles made by edges of this conductor or edges of this charge distribution with respect to the point of interest are, one is theta 1, the other is basically theta 2. Okay. So in that case, the expression is given by rho L, which is charge density source, divided by 4 pi epsilon times rho, which is distance, into cos of theta 1 plus cos of theta 2. What is the direction here? Radial direction, but radially away from axis, z axis. So radially away from z axis, what is the direction you are having? Direction is nothing but rho cap. Here look at the direction, r cap radially away from origin. Here rho cap means radially away from z axis. Okay, and without epsilon you will have the expression for d bar. Okay, next special, the moment you remember this previous case, no, this finite length line charge scenario, semi-infinite length, infinite length, both are special cases. Okay, so here we have semi-infinite length line charge. When you join the edges of the conductor, okay, this is one edge, edges of the conductor with respect to the point of interest. What is this angle right now? This angle theta 1 tends to 0 degrees, because if I ask you what is tan theta is nothing but this finite length obviously by infinite length, because how much is the length of this guy? The end is present at infinity. So because of that, yeah, finite length, non-infinite length divided by infinity is nothing but 0. So tan of an angle is nothing but 0 means angle is nothing but 0 degrees. What about the other angle, this one, theta 2? Theta 2 is nothing but 90 degrees here. Okay, and this distance, the radial distance between the conductor and the point of interest is taken as some rho. Okay, so this is rho. So in this case, yeah, rest all things are same as previous case. Only thing is, in the cos terms, cos theta 1 is nothing but 0, theta 2 is 90. So this term is gone, this term becomes equal to 1, because cos 0 is nothing but 1. So 1 plus 0 is nothing but 1. So this entire bracket term becomes equal to 1, and coefficient is rho L by 4 pi epsilon rho. That part remains. Okay, that part anyway remains. So rho L by 4 pi epsilon times rho, direction is nothing but rho cap. Okay, and next infinite length line charge. This is one scenario that you are supposed to remember. If nothing is mentioned, the line charge means infinite length line charge only. Okay, so this is basically by default line charge. If nothing is mentioned means the line charge is basically infinite length line charge. Okay, in this case, both ends are where? Both ends are at infinity. So whenever one end is at infinity, the corresponding angle becomes how much now? 0 degrees. Here also the other end is also at infinity. Means theta 2 also tends to how much? 0 degrees. So in the previous case, the bracket terms, if you substitute both theta 1 as well as theta 2, both being equal to 0, then what do we get? Cos 0 is nothing but 1, 1 plus 1 becomes equal to 2, 2 by 4 is nothing but 2 in the denominator. So that is what is the expression we have here, rho L divided by 2 pi epsilon times rho. Without epsilon is what you have in that expression. Okay. Yeah, ring charge not so important from gate point of view. So if you want to, remember this, up to you. But anyway, I'll just explain this. You have a ring with a charge density of rho L coulombs per meter. So the charges are present on this ring. Okay, on this ring is where the charges are present. Okay, with how much amount of charge density, so and so value. What is the radius of the ring? That is nothing but a. At a distance of some h meters away from the center. So this is the center of the ring. Away from center, at what distance? At h meters away from the center, you have taken the point of interest. There, what is the value of electric field intensity? So the formula is given by rho L AH divided by 2 epsilon A square plus H square. Sometimes they will ask you what is the expression of electric field intensity at the center. Okay, so this guy, okay, this guy E bar at center O. Okay, center is nothing but O. What will happen? At the center, this H distance becomes equal to 0, right? Yes. So what happens is nothing but at center, H becomes 0. Means what is electric field also becomes equal to 0. So in case of ring charge center electric field intensity value is nothing but 0. Okay. Ring current, the magnetic field intensity at the center will not be 0, but electric field intensity at the center of ring charge becomes equal to 0. Okay. Do remember that. Yeah. But yeah, so not so important from GATE point of view this one, because we never got a question on this. Kind of far-fetched. Mostly we'll get infinite line charge, and then we get point charge placed at origin, point charge not placed at origin. These two scenarios we'll get. Okay. And then volume charge. Lastly, we have seen volume charge. That is also something that we will get. And lastly, we are having one more thing, sheet charge. So in this sheet charge scenario, this sheet that you have, here is nothing but the sheet charge having a charge density of rho s coulombs per meter square. So this is the place where you are placing all the charges on a particular surface. You are placing charges on a surface. Let's assume on xy plane. On xy plane. So in that case, what is the value of electric field intensity? Electric field intensity, or initially we look at flux density, easy to remember. Flux density is simply half of the charge density. Rho s by 2, either z cap or minus z cap. In both cases, if you notice, the common thing is nothing but, okay, the direction is away from the sheet. Away from the sheet. Okay. Z greater than 0 means above. Okay, so this region corresponds to above the sheet, and Z less than 0 means you are below the sheet. Okay, here whenever we say that charges are present on xy plane, okay, xy plane has what equation? Can I say that equation is nothing but Z equal to 0? Yes. So above the sheet means Z greater than 0, below the sheet means Z less than 0. Okay. So if you take a point above the plane, what is the direction of that particular electric field intensity or electric flux density? That is nothing but z cap. And if you take a point below, what is the direction of electric field intensity? It is nothing but minus z cap. So whether it is plus z cap or minus z cap, the common point is nothing but the electric field lines are basically going away from the sheet charge as such. Okay. And the expression of magnitude of flux density becomes how much? Half of the charge density. So you can understand that half of the total I placed rho s amount of charge density, half of that charge density is producing flux lines on the one side, the other half is producing flux lines on the other side, and divided by epsilon is nothing but electric field intensity. So this expression becomes equal to expression for E bar, and this is the expression for D bar. Same as the previous case also, here also these are the expressions for E bar and these are the expressions for D bar. You can notice that in all these cases, electric field intensity is a medium dependent quantity because E bar is proportional to 1 by epsilon, but D bar has no epsilon term in them. So due to which we can say that here D bar, okay, that is electric flux density, is independent of medium. Whereas electric field intensity is basically dependent on medium. More so, in what manner? E bar is proportional to always 1 by epsilon. Okay, it's inversely proportional to the dielectric constant. So you choose the better dielectric constant. Higher dielectric constant means electric stresses will reduce inside a material. Okay, yeah. Next, we'll look at a few problems now on this. Few simple problems. So a charge is distributed uniformly over the plane z equal to 10. So the plane here is nothing but z equal to 10. Okay. So since we have taken the plane as nothing but z equal to 10, now you will have two parts, z greater than 10 and z less than 10. Okay. So in this context, since plane is z equal to 10, z greater than 10 means above. So this is above the plane and this is below the plane. This is below the z equal to 10 plane. Now the charge density is given as 1 by 3 pi nanocoulombs per meter square. Find the magnitude of electric field intensity for z less than 10. I also want direction. Okay, here in this case I also want direction, let's assume. So z less than 10 means basically below. below. Now what is the expression for E bar below? E bar below how much? Magnitude is how much? Rho s by 2 epsilon. So nothing is mentioned about the medium, so means we can assume free space. Free space means epsilon naught. And direction is what? Direction is minus z cap. Why minus z cap? Because you have taken below. So sometimes options can be given with direction also. So hence I am giving the answer with direction here. What is rho s? Rho s is equal to nano coulomb we are having means 10 power minus 9 by 3 pi. This is 3 pi. Okay. So numerator part is complete. 2 into epsilon naught. So what is the value of epsilon naught you will take? Yeah, most of you will be taking 8.85 into 10 power minus 12. But I've given you one more expression, that is 10 power minus 9 by 36 pi. Take that value. Okay. So this is now 10 power minus 9 by 36 pi. Okay, 36 pi. Direction is minus z cap. It will greatly help you reduce the calculations. So 10 power minus 9, 10 power minus 9 is gone. And overall now this becomes equal to 36 pi goes to the numerator. So this is 36 pi divided by 2 into 3 pi is nothing but 6 pi. Okay, direction is minus z cap. And hence the answer is now 36 pi by 6 pi is nothing but 6. 6 into minus z cap. Units for electric field intensity is what? Volts per meter. Okay. So answer is nothing but 6 into minus z cap. A simple problem if you see. But the answer becomes very simple, calculation becomes very simple if you take the proper value of epsilon naught here. And the value of epsilon naught you are supposed to take here is how much? 10 power minus 9 by 36 pi. Okay. Yeah, good. Good. I want you guys to solve the questions. Okay. Now, this is a previous GATE question, similar model now. Infinite plane is present where at y equal to 6 meters. So now you are having y greater than 6 one region, y less than 6 one more region. And the associated electric field strength is dash. Electric field strength is, see, directions are not given. Okay. So since y equal to 6 is given, so direction of E bar in this scenario. Okay, what do you think are the directions? When z is constant, direction is plus or minus z cap. So when y is constant, directions will be what? Plus or minus y cap. Plus or minus y cap. Okay, so that itself is sufficient to eliminate two options, because this is I cap and this is k cap. Okay, so because of this reason, this is not the correct answer. This is also not the correct answer. So A and C are gone on the basis of just direction. I don't even have to do the magnitude calculation here. I can nicely eliminate two options. Okay, my answer now is in terms of either B or D. So let us find out whether it is B or D. Okay. Now, what is the magnitude? E. E due to a sheet charge. E due to a sheet charge becomes equal to, this is rho s, just magnitude if I want, rho s by 2 epsilon, right? So rho s value is how much? 1 by 6000 pi divided by micro. Micro means 10 power minus 6 divided by 10 power minus 9 by 36 pi. Okay, and into 2. When you do the calculation here, 1000, no? So 1000, 10 power minus 6 becomes 10 power minus 9, denominator also 10 power minus 9 gone. So then this becomes equal to 36 pi divided by 2 here, and 6 pi here, means 6 into 2 is 12 pi. So magnitude is nothing but 3 volts per meter. In what direction? Direction is plus or minus j cap. Plus or minus j cap, and yeah, I can choose, because of that answer is nothing but B. Now what if one of the option is basically minus minus 3 j cap? Okay, what if you are having both options, 3 j cap, 3 minus j cap? So you have to see whether the question is MSQ or MCQ. So if they gave you both answers, 3 j cap as well as 3 minus j cap, so probably that question was given as MSQ. Okay, if it is not MSQ, then you have to reread the question and see whether a point is given to you or not. Here in this case, point is not given to me. Y greater than 6, y less than 6, nothing of that sort is given to me. So I can assume ki, yeah, point can be anywhere. So if point is anywhere, in that case, plus y cap is possible, minus y cap is also possible. I'm looking at only possibilities here. Okay. Yeah, so this is regarding the infinite sheet charge. Yeah, good. B, correct. Yeah, one more question. This is in fact a recent question of GATE 2024 question. This is, you have been given 3 point charges. Please look at what is the model here. You have to first tell me this question belongs to what model. This question belongs to what model? You have to tell me the answer now. No, no, no. Which kind of charge distribution? Point charge, line charge, surface, volume. What kind of distribution this is? So yeah, this is a point charge scenario, correct? But point charge present where? Are the charges present at origin? Maybe one charge, none of the charges are present at origin. So you don't have any charge placed at origin. So this is the scenario of point charge but not placed at origin. Okay. So then how do you solve this question now? So first we will take the locations of all the 3 charges. The 3 charges I am having are, I will call it as 1, this is 2, this is 3. Okay. And yeah, this is the location of the charge Q1. So from this we'll have R1 bar, from this we'll have R2 bar, and from this we'll have R3 bar. Okay. This is the point of interest, right? So this is point P. This is point P. So now we'll have 4 position vectors. The first is nothing but R bar. So from this, what is R bar? 0 x cap, 0.5 y cap, 0 z cap. So overall becomes equal to 0.5 y cap. And similarly, what is R1 bar? What is R2 bar? What is R3 bar? R1 bar. Okay, for this guy, what is R1 bar? Minus 1 x cap, 0 y cap, 0 z cap means minus x cap. And R2 bar, 1 x cap, 0 y cap, 0 z cap means this is simply x cap. And this is 0 x cap, minus 1 y cap, 0 z cap means this is minus y cap. Okay, the third one is minus y cap. Now, I want finally E bar, electric field intensity at point P. What is electric field intensity at point P? It is because of electric field intensity at point P because of 3 charges, E1 bar, E2 bar, E3 bar. That is EP at point electric field at point P because of charge Q1, because of charge Q2, because of charge Q3. All the 3 components. Okay. Yeah. So what is EP1 bar? This is Q1 divided by 4 pi epsilon. I am making use of now formula. Electric field intensity due to a point charge not placed at origin. Okay, Q1 by 4 pi epsilon into R bar minus R1 bar divided by the modulus value whole cube. Okay, next this is Q2 divided by 4 pi epsilon R bar minus R2 bar divided by the modulus whole cube. Lastly, this is Q3 divided by 4 pi epsilon R bar minus R3 bar divided by the modulus whole cube. And ultimately you have been told that electric field intensity at the point P is nothing but 0. So overall this expression becomes equal to 0 as per the given data. Okay, as per the given data. Means, yeah, whatever is this, 1 by 4 pi epsilon terms we are having, no, I can cancel them out. Okay, I can cancel this 1 by 4 pi epsilon, 1 by 4 pi epsilon, taken common, thrown onto the other side. Next, what is Q1, Q2 and Q3? They are nothing but first one is Q. So now we can substitute the data. Yeah, first one, Q1 is nothing but Q. What is R bar minus R1 bar? R bar is 0.5 y cap, R1 bar is minus x cap. When you take the difference, so that becomes equal to 0.5 y cap minus of minus is nothing but plus x cap divided by square root of 0.5 square plus 1 square. Magnitude is what you are supposed to take, whole cube. Okay, so this magnitude whole cube. Anyway, we will do one thing. We will calculate first of all separately what are r bar minus r1 bar, r bar minus r2 bar, etc. So what is here in this expression, r bar minus r1 bar first of all, and r bar minus r2 bar, and r bar minus r3 bar. Yeah, all these three terms. What is r bar minus r1 bar? This is nothing but x cap plus 0.5 y cap. And what is r bar minus r2 bar? Minus x cap plus 0.5 y cap. And what is r bar minus r3 bar? So this is 0.5 minus of minus is nothing but 1.5. So this is 1.5 y cap. Okay. And in all the cases, what is their modulus? What is their magnitude? Magnitude is square root of 1 square plus 0.5 square. What is 0.5 square? 0.25. So this is square root of 1.25. Same story here also, this is square root of 1.25. Magnitude of 1.5 itself is nothing but 1.5 only, no? This is 1.5. Okay. So now you can substitute these values in the previous expression here. So then you will get Q1 here is nothing but Q. So this is Q into minus, or sorry, x cap plus 0.5 y cap divided by 1.25. Square root means whole power half, again whole cube you are having, means whole power 3 by 2 plus q into minus x cap plus 0.5 y cap divided by 1.25 whole power 3 by 2 plus the last term is nothing but alpha q. Okay, that is what is given, alpha q, q3 into what is r bar minus, this is 1.5. So into 1.5 y cap divided by 1.5 whole power 3. And ultimately this becomes equal to how much? 0. Here if you notice, x components are supposed to be added, y components are supposed to be added. Plus x cap and minus x cap have the same coefficients. Coefficient here is what? Q, there also Q, denominator is what? 1.25 whole power 3 by 2, say they're also same story. They're all gone. So then if you do the calculation there, all that is left out is nothing but, I can also further cancel out the Q terms here. Okay, now the only thing that is remaining is nothing but in the first part, we have 0.5 divided by 1.25 whole power 3 by 2. Then the next term is again plus 0.5 divided by 1.25 whole power 3 by 2 plus alpha into 1.5 by 1.5 whole cube. Okay. So these are the terms you are having. If you notice, first one is what? Y component, 0.5 by 1.25 whole power 3 by 2. Here also 0.5 by 1.25 whole power 3 by 2. The last one, if you notice, alpha into 1.5 divided by 1.5 whole cube. Okay, whole cube. Yeah, so overall, this is the y component and this has to be equal to 0. So means what? Y component also has to be 0. So when you do the calculation now, finally the value of alpha becomes equal to minus 2 into 0.5 divided by 1.25 whole power 3 by 2. If I do the cancellations here, okay, 1.5 as plus 1.5 whole cube is nothing but 1.5 whole square. So is what you are supposed to send to the other side into 1.5 whole square. Okay. So please do this calculation now. It becomes a simple calculation now. 2 into 0.5 is nothing but 1. See, while, okay, you got the answer. You should get a negative answer. Negative answer minus. 1.61 is what I got. Please cross verify. Yeah, good. 1.61. So if you see the question as such, it's a very simple question, but the logic, you have to understand the, what is the heart of the problem. The heart of the problem is nothing but this formula. Okay, that is nothing but electric field intensity at a particular point of interest because of a charge not placed at origin. Yeah, now I have taken a charge and the charge is not placed at origin. So that is the case you are supposed to consider here. Okay. Right? Yes. Let's go for the next topic, next question. In fact, next topic. Next, we have another very important topic, which is electrostatic potential. Okay. So, electrostatic potential at any point is defined as work done in placing a charge at that point of interest brought from infinity divided by the charge value itself. Or in simple terms, you can understand that electric potential is basically work done per unit charge. Okay. So, hence, V, if you notice, V is basically W by Q, which is work done per unit charge. So here we have the expression as nothing but work done per unit charge. Hence we have taken the expression as nothing but W by Q. Okay, so here the expression is basically W by Q. And what is the expression of work done here? Work done is, taken basically as nothing but force into distance. Yeah, you can take it as force into distance if at all force is constant. But what if the force is not constant? In that case, you have to take integration. And what integration you are taking? This is line integration. Okay. Along the path you are moving, you have to perform line integration. And why you are taking minus sign here? Because the force is nothing but force is the force acting. Okay. So you can have two kinds of forces. One is nothing but force applied and force acting. So if you take force applied, then yeah, you have to take plus sign. But since the force is nothing but force acting on the charge, so I am taking that minus sign here. Okay. Since in this case force is nothing but force acting. Okay. And already we have seen that in case of electric field intensity definition, what is force? What is force? Force is nothing but Q times E bar. Force acting on a small q charge is given as Q times E bar because of electric field. And when you take that, the Q in the numerator as well as denominator is gone. And finally, we have potential expression as nothing but minus integration of E dot dl, which is basically certain line integration. So some kind of a line integration. So you have to understand that if you integrate E, we are getting V. Reverse is what? If you differentiate V, we get E, right? Yes. So when you differentiate on both sides, what kind of differentiation you can do it on scalar function? We know that gradient only, and that's what I'm taking. Gradient of V becomes equal to now minus E. Okay. So the next expression you have is nothing but E bar becomes equal to negative of gradient of V. Okay. And by using this formula, if you want to find out potential difference between 2 points, that is V1 minus V2. Okay. So in this case, whenever I say V12, I mean to say V1 minus V2. Okay. 1 is always upper limit, the positive term is always upper limit, 2 is always a lower limit. Okay. Negative term is always a lower limit. Remember, 1 upper limit, positive term upper limit, negative term lower limit. So that is the expression for the potential difference between 2 points on the basis of potential expression. Okay. Yeah. Now let's look at a few problems on this. So this is a straightforward question. This is basically a straightforward question. Okay. So given potential function, we have been given V of x, and we are supposed to find out what? We are supposed to find out the magnitude and direction of electric field intensity at a given point in space. So V was given, you are supposed to find out E. And what is the formula linking both? The formula linking both is nothing but E bar is equal to negative of gradient of V. Okay. So whenever you take gradient of the function is given in terms of rectangular coordinate system. What is the formula for gradient? Dou V by dou x x cap, dou V by dou y y cap, plus dou V by dou z z cap. Okay. And yeah, when you take differentiation of V with respect to x, what do we get here? 100x. So this is 100x x cap differentiate the function with respect to y. Here there is y term, differentiation of 50 y square with respect to y is 100 y cap, and differentiation of z component with respect to z is, that is 150 z square, differentiation with respect to z is 100 z, and this is z cap. Okay. Now you have been given a point of interest 1 minus 1 1. So the point of interest is 1 minus 1 1. If you substitute, what do we get? X is nothing but 1. So 100 into 1 is 100, minus n you are having. So minus 100 x cap, and y is nothing but minus 1. So we'll get minus 100, and again minus of minus 100 is nothing but plus 100. So plus 100 y cap, and z component is 100 into 1 minus sign again you having, means minus 100 z cap. Okay, so this is basically the expression of electric field intensity. Okay, and you have been asked what? Direction, as well as also given the potential function, dimensions, magnitude and direction. See, if nothing is mentioned, direction means what always? Unit vector only. Direction is always a unit vector, right? If nothing is mentioned. Okay. So then for this guy, what is the magnitude? Calculating magnitude for this guy is not a big deal. Magnitude is 100 root 3. I can clearly see that this is 100 root 3. Okay. And what about direction? What about direction? This vector by 100 root 3, which becomes equal to minus x cap plus y cap minus z cap divided by root 3. Okay. So finally the answer is it B or D? It is nothing but D. Okay. So it's a simple formula now. All you have to remember is nothing but, remember the name of electric field intensity. What is the name of electric field intensity called as? Potential gradient. Okay. Why it is called as potential gradient? Because you are obtaining this by taking gradient of potential. On the RHS, what you are having? On the RHS, you are having gradient of potential. Gradient of potential. Okay, with a negative sign. Okay, and hence we are calling electric field intensity as nothing but potential gradient. So again, this is a straightforward formula based question. You will get these kind of questions a lot in exam. Now this is one important model. I am taking this problem specifically to explain one main concept here. The main caution that you are supposed to take while doing these problems are, in line integration problems, in integration of, let's assume, a bar dot dl bar expressions, okay, duplicate terms should be removed. In the result, remember this point basically, duplicate terms must be removed. So remember this note point, because sometimes examiners may play that small trick on you. Okay, they will just see whether you are able to do this line integrations properly or not. So in this case, what is the formula for potential? Here you have been given electric field intensity, and what you are supposed to find out? Electrostatic potential. And electrostatic potential in our language is what? V. So how do you get V from E? Just now we have seen that V becomes equal to minus integration of E bar dot dl bar. Okay, so the given function is in terms of rectangular coordinate system. In rectangular coordinate system, what is the expression for dl bar? What is the expression for dl bar here? Dl bar is dx x cap plus dy y cap plus dz z cap. Okay, so whenever you take this dot product and write the expression becomes equal to minus minus plus. Again, if you take minus sign, so then it becomes plus plus minus, reverse. Okay, so this becomes equal to plus sign here, first one. First integration is 2y cube minus, this is the x component, no? 2y cube minus 3yz square. Okay, 3yz square. The first one is integration with respect to dx, because x component here is nothing but dx, first integration. Second integration, integration of minus is gone again, so we have 6 y square minus 3x z square. Now the second one is integration with respect to only y dy minus of plus is minus integration of 6xyz okay, and integration with respect to z. So this is what you have. Now perform the integrations. How many integrations you are performing here? Total 3 integrations. What are the 3 results? Let's verify. You are integrating only with respect to x in the first case. So means this is 2xy cube. There is no x term here. There is no x term here also. So minus 3xyz square. So this is the result of the first integration. What is the result of the second integration? Okay. Integration of 6xy square with respect to y becomes how much? Yeah, 6. I think there is a small issue with okay. What is the integration of 6xy cube? Correct only. So y cube by 3 will get, and 6 by 3 is nothing but 2. So this is 2xy cube. 2xy cube minus, what is the second term? There is no y term here. So this is 3xyz square. Okay, plus I am taking this minus sign inside. What is integration of z with respect to z? Z dz integration is nothing but z square by 2. 6 by 2 is nothing but 3. So we have this term as nothing but minus 3 xyz square, right? So this is what you have. Now look at the individual terms. This point we will apply right now. So 6 or 2xy cube. Do we have this term repeated? Let's verify. 2xy cube, yes, repeated means remove it. So this is a duplicate term. Any duplicate terms, we'll remove it. This is now minus 3xyz square. Do we have it second time? Yes, remove it. Yes, remove it also. So any duplicate terms that you see in the result of this integration, you have to remove those duplicate terms. Then only you get the proper answer. Okay. So in this case, finally, the proper answer for potential function v becomes equal to 2xy cube minus 3xy z square. Okay, 3xy z square. Okay, so this is the expression for potential here, and if you look at the options, 2x y cube minus 3xy z square. Okay, so that is the correct answer. So wherever in this line integration you see duplicate terms, always remove the duplicate terms. Okay. Next, solve this question. Again, we have been given V potential, and we are supposed to find out expression for electric field intensity. If there is 3xy cube, see, if there is only 3xy cube, you don't have to remove it. You will definitely have to include it. Okay, in this term, let's assume there is another term, maybe some here. Let's assume extra term you are having 3xy cube. Okay, someone asked me a question. If this is there, then we don't remove this term. We will keep this term in the final answer also. Okay. Any duplicate terms, individual duplicate terms you are having means only those terms you will remove. Okay. Only duplicate terms should be removed, nothing else. Because see, you are basically in a way performing 3 integrations of the same quantity. Okay. 3 integrations of the same exact quantity. So because of which you are getting duplicate terms. Okay. Definitely there is a possibility of you getting duplicate terms. It's not necessary that every time you will get duplicate terms. Sometimes you may not get duplicate terms also. Okay. But yeah, if there are duplicate terms, the duplicate terms are because of the fact that you are integrating that same term 3 times. Okay. So integrating that same term 3 times. So because of which you are getting the duplicate terms. Okay. Again, there is a different way actually of solving this problem also, but I don't want to go into that method. It's a bit lengthy method, not a discussion for now. Okay. Usually in the normal class, routine class, I discuss that method also, but now this is not the time for discussing that method. Okay. Yeah. Now go to the next question. Here, what is the logic? You have been given potential function, which is nothing but phi, which is phi. In our language, I will call it as V. Potential function is known as V by me usually. So V is given, and what you are supposed to calculate? The magnitude of electric field at so and so point x equal to y equal to 1. Units is what? Volts per meter. So volts per meter means E bar. So you are ultimately supposed to find out E bar magnitude. Okay. So how E bar and V are related? E bar is equal to negative of gradient of V. Negative of gradient of V. Okay. So yeah, rectangular coordinate system, xy parameters only. So this is minus dou V by dou x, x cap, less dou V by dou y, y cap. When you differentiate this function with respect to x, we get 2 root y. So minus 2 root y x cap. When you differentiate that function with respect to y, square root of y is nothing but y power half. So this is 2x into half into y power minus half y cap. Okay. So when you differentiate square root of y, so this is the result of that integration y cap, right? Now I got electric field intensity expression. Point you substitute, x comma y becomes equal to how much now? This is equal to 1 comma 1. If you substitute this data, we get the answer as what? Minus of 2 root 1 becomes equal to 1 only. So 2 into 1 is nothing but 2. So this is minus x cap minus 2x cap. Here 2 and 2 is gone, and x is equal to 1. Y is also equal to 1. So 1 into 1 power minus half is nothing but 1 only. So all you get is nothing but 1 only there. So minus, if you send it inside, minus y cap. So finally you get it as minus y cap. Okay, this is the answer. And from this, what is the magnitude? What is the magnitude of this guy? Square root of 4 plus 1 becomes equal to square root of 5. Okay, so in this case the magnitude is nothing but square root of 5. Simple problem, right? Yeah. So these questions, no, you should not miss. No matter what, these are very simple questions. Okay, all you have is this formula, gradient of V, negative sign is nothing but electric field intensity. So these questions must be answered by you at any cost, no matter what. Yeah, root 5, good. Next, solve this question. This is a good question. Let me see how many will be able to solve this question. I'll give you 2 minutes of time for solving this question. You try it on your own. Okay, you try it on your own first. So potential function is given in the form of a diagram. Until now we are having potential functions given as an equation now. Now here potential function is given as a diagram. By using this they are asking you, sorry, not potential function, electric field intensity expression, E bar is given to you as a diagram, and by using this they are asking us what is the potential difference between 2 points. This was a 2-mark question basically. It was a 2-mark question. Okay. You see, EC students generally believe that they don't have to study the statics portion. But if you see, a lot of statics portion, questions are getting, we are getting in EC paper. Every year, at least 2 to 3 marks will get only from statics portion. Okay. And the questions that EC students will get from statics portion, they are not tough. They are very easy questions, very basic questions. Okay. Okay. So here you can notice that y-axis is nothing but E. So this is y-axis, let's assume this is nothing but electric field intensity. in terms of volts per meter or kilovolt per centimeter. Okay, so anything is up to you. Okay, so let me convert all these numbers in terms of volts per meter. Volts per meter. So this 20 kV per centimeter. kV means what? 10 power 3. So this is 20 into 10 power 3 divided by centimeter means 10 power minus 2 meters. So finally I got the answer in terms of volts per meter. So what do we have? I can say that this is nothing but 2 into 10 power 0 here, 3 zeros here, and 2 zeros in the denominator means a total 10 power 6. 10 power 6 volts per meter. Okay, I can write it like this. Or I can also write it as basically 2 volt per micrometer. Okay, 2 volt per micrometer, because if you notice here, I have been given this data in terms of micrometers, hence I am writing like that. Now, y-axis is nothing but E. What is x-axis now? X-axis is nothing but distance. I can take this point as reference. This is x equal to 0 and this is x is equal to 5. Now I am taking x in terms of only micrometers only. This is entirely in terms of micrometers. So 20 kV per centimeter is also equal to 2 volts per micrometer. So then what is 40 kV per centimeter as? 40 kV per centimeter is nothing but 4 volts per micrometer. I can write it like this, no? So entire horizontal discussion is in terms of micrometers. Vertical electric field intensity is in terms of volts per micrometer only all the time. Okay. So that unit mismatch is not there right now. Okay. Now I want to get the equation for E. So is it not now a straight line having some y-intercept? Yes, we all know that y is equal to what? Can I say mx plus c? Yes. In this case, y is nothing but electric field intensity E. X is nothing but distance parameter only. Slope, what is the slope value? Slope is nothing but y2 minus y1 by x2 minus x1. Okay, that is the vertical change divided by horizontal change. How much is the vertical change here? 5. And what is the, horizontal change is 5. And what is the vertical change? This is total 4 and this is total 2. 4 minus 2 is nothing but 2. Okay, and hence what is the slope here? The slope in this case becomes equal to 2 divided by 5, okay, times x plus y-intercept. What is y-intercept? The intersection of the line on the y-axis. So this corresponds to, can I say c only? Yes, y-intercept, which is nothing but how much value? 2. So that becomes equal to 2 plus 2. That's it. But please notice that we are taking here x in terms of micrometer and whatever answer we are getting is in terms of volts per micrometer. So I got the expression for E now. E is equal to 2x by 5 plus 2. Okay. In this expression, x in micrometer and E in terms of volts per micrometer. Okay. That's it. I got the expression for E. Now on the basis of this, can you calculate the expression for V? Yes. What is the expression for V? V is equal to minus integration of E dot dl minus E dot dl, which becomes equal to how much in this case? This becomes equal to minus, there is only, the direction of electric field also I am supposed to take. Nothing is mentioned here. Since this is assumed as nothing but x, we can assume that the electric field is only along x cap direction. On the basis of this, this E bar is nothing but, this is along only x cap direction. So since this is along x cap direction, when you take dot product here, we get the term as what? 2x by 5 dx plus 2 into dx plus 2 dx. So this is the integration you are doing. Okay. Now please perform the integration. When you perform the integration, 2x by 5, x dx integration is 2 by 5 x square by 2, one term, and one more term is nothing but second term is 2 dx. 2 dx integration is nothing but 2x. So this is nothing but 2x. The limits of the integration is from where to where? This is anyway the minus sign is nothing but potential function. Okay. So finally from the expression given to me, from the diagram given to me, I got the expression for electric field intensity. Now I am using the formula. Okay. Now perform the integration. When performing the integration, you got this answer. I got now potential function. Okay. So this is basically potential function. What do you want from the data? You want basically phi b minus phi a. At the point B, if you notice, what is the value of x? X is nothing but 5. At point A, what is the value of x? X is nothing but 0. Okay. So because of that, if I want VB minus VA, this becomes equal to minus, I can take common. VB means substitute the value of x as nothing but 5. Okay. So by the way, here 2 and 2 is gone. I can write this as minus of x square by 5 plus 2x. Okay. So minus I'm taking outside. So this is 5 square by 5 plus 2 into 5. This is for B, because at B the value of x is nothing but 5. At A the value of x is 0. Okay. Minus 0. On the outside anyway you are having a minus sign. Okay. So finally becomes how much now? 5 square by 5 is nothing but 5 plus 25 is 30. So this is minus 30. Okay. So this is the, sorry, 2 into 5, no, I'm sorry, 2 into 5 is 10. So 2 into 5 is 10. So 5 plus 10 is 15, minus 15, I'm sorry. This is minus 15. Okay. So the logic, EMF logic here is not tough. It's very simple. All that we have here is nothing but, yeah, get the expression for electric field intensity now. That was not directly given to you, that was given as a diagram. Okay. And by using that, we are supposed to calculate the expression for V by using the logic that V is equal to minus E dot dl. And after you get the expression for V, all you have to do is nothing but take potential difference between the 2 points given to you. Okay. So this is about this problem. So writing this equation of the line as nothing but y equal to mx plus c. That is the most important part. If you are able to do that, the problem is complete. Right. Yeah, good. Jayant, one more logic is nothing but area under the graph. Because see, when you take V equal to minus E dot dl, don't you think E dot dl, whenever you perform integration, don't you think you are getting area under the graph only? Yes, you will get area under the graph here. That is also one more logic. It works, but definitely it will give you the magnitude. What about the sign? Okay, what about the sign? Positive sign or negative sign? What do you take? So there again you have to be cautious. Yeah, you got the potential difference magnitude. You will get whenever you find out area under the graph also, no? This is a trapezoid. Trapezoid, I hope you know the formula, half h times a plus b. When you do that, you will get the answer now also as nothing but 15 only. Okay, but whether to take positive sign, negative sign, again there might be a confusion. Okay. So this approach will definitely avoid that confusion. But yeah, approach is correct. There is nothing wrong with the approach. Area under the graph will give you the result of this particular integration. Okay, integration basically will give you what? Area under the graph. Okay. Let us go for the next question. Next one is a very simple one. Here, there is a point charge, 1 nanokilometer point charge, and the potential. Okay, to answer this, I'm sorry, we have to also discuss one more small concept. And for this, yeah, this one. Okay, potential due to a point charge formula as well as potential difference because of line charge. Amongst these two, again, the first one is important. Remember the first one. What is the potential formula because of a point charge? Let's assume there is a point charge like this for you. This is a point charge having a charge magnitude of, let's assume, q. And far away there is a point of interest. This is a point of interest. How much is the distance between both of these guys? R. So because of this charge at this point, what is the value of potential? So V basically at P due to Q. Okay. So that is basically this formula given by Q by 4 pi epsilon times R, where R is the distance between the charge as well as the point of interest. Potential is basically a scalar quantity, hence obviously there is no direction. See, if you want to derive it also, it's not a big derivation, very simple derivation only. What is the formula for V? V becomes equal to minus integration of E dot dl. And what is the expression for E bar in case of the point charge? This becomes equal to minus integration of Q divided by 4 pi epsilon times r square r cap dot, what is dl bar then? Since E bar is along r cap, you will take this guy also as nothing but r cap component only. Okay, so r dot r is nothing but 1, dr by r square is the integration that you are doing. Q by 4 pi epsilon, I can keep it outside, minus dr by r square becomes how much? That becomes equal to 1 by r, okay, which is basically q by 4 pi epsilon times r. So I'm just telling you that even if you forget this formula, it's not a big deal to derive it. In examination hall also, 2-3 steps you'll get your answer. The basic formula here also is what? V is equal to minus E dot dl. That is the basic formula. And whenever we have a line charge scenario, here when I say line charge, I mean to say infinite line charge I am taking, okay. Because of infinite line charge, what is the value of potential difference between the 2 points, okay. So that is given by V12 becomes equal to minus integration of 1 to 2 E dot dl, no, okay. And what is the expression of electric field intensity because of line charge? Remember the formula, rho L divided by 2 pi epsilon times rho, direction is rho cap. So since E bar is along rho cap direction, dl bar will be also along rho cap direction. D rho by rho integration becomes how much? Ln of rho, okay. You are integrating from 1 to 2. So this becomes equal to rho L divided by 2 pi epsilon can be taken outside. So d rho by rho integration is nothing but ln of rho, okay, with a minus sign overall. And the integration, this is 1, this is 2. So 1 means the value of rho becomes equal to d1, and at point 2 means the value of rho becomes equal to d2. So when you substitute the limits, initially you will get d1 by d2. If you take the minus sign inside, so finally you get the answer as nothing but ln of d2 by d1. So these are the two formulae. Remember the formula, and derivation also hardly will take half minute of time or 1 minute of time, not more than that. Simple derivations only. So do also derive, even though it's just before the exam also you can derive this half minute, 1 minute formula, right? Okay. So these are the two important formulae. Now on the basis of this, let us answer this question. Yeah. So there is a charge, 1 nanocoulomb charge. This is nothing but Q. Because of this charge, I want to find out VPQ. What is VPQ right now? VP minus VQ is what you are supposed to find out, right? Yes. So I want to find out here VP minus VQ. Yeah, so this is VP, Q is nothing but VP minus VQ. VQ is equal to. Yeah, what is the potential at point P? That is given by, this is Q divided by 4 pi epsilon times R P minus Q divided by 4 pi epsilon times R Q. Okay, so I can take 1 by 4 pi epsilon common. What is 1 by 4 pi epsilon naught? If nothing is mentioned, medium is nothing but free space. 1 by 4 pi epsilon naught is nothing but 9 into 10 power 9. So this is basically 1 by 4 pi epsilon naught common value. Charge value is also given, 1 nanocoulomb means 1 into 10 power minus 9. So this is basically Q into, now you are taking 1 by Rp minus 1 by Rq. What is Rp and Rq? Rp is nothing but 40 millimeters. So this is the 1 by 40 millimeters. I am writing it directly. I have to write everything in terms of meters. What is millimeter? 10 power minus 3 meters. So 1 by 40 into 10 power minus 3 becomes equal to, can I say, 1000 by 40 here, yes, minus the second term is 1000 by 20, okay. So this last part of the problem is basically, this is 1 by Rp minus 1 by Rq in terms of only meters, in terms of meters, okay. So when you do the calculation, 1000 by 40 becomes how much? So this 1000 by 40 becomes equal to 25, I believe. No, yeah, 25. So this is 25 and this is 50. 25 minus 50 is minus 25. So 10 power 9, 10 power minus 9 is gone. 9 into minus 25 becomes minus 225. So answer is nothing but B, minus 225. So when you do the calculation here, finally this becomes equal to minus 225 volts, right? Yeah. A simple question again. All you have to remember is nothing but The formula by 4 pi epsilon times r. Right? Okay, solve this question, guys. Solve this question. So we have a plane y equal to 2 carries infinite sheet of charge 4 nanocoulomb per meter square. If the medium is free space, they have already specified the medium also has nothing but free space. What is the force on a charge of 5 millicoulomb? Okay, so this is the charge given to us. Let me call this charge as nothing but small q charge. So this charge is nothing but small q charge. So we have to find out force acting on q. What is the expression for force acting on q? Why force is acting on q basically? Because of electric field. Okay, is equal to, can I say this is nothing but q times E bar? Yes. What is E bar now? Electric field acting on q. So this is nothing but E bar electric field acting on q. Okay, on q. So on q, electric field is because of whom? Because of other guy. Okay, which is nothing but y equal to 2 infinite sheet charge. E bar on q due to the other source that you are having, which is nothing but infinite sheet charge. Infinite sheet charge. Okay. So I have already the expression for q. Now I have to get the expression for E bar. Just now we have seen that in case of infinite sheet charge, what is the expression for E bar? So this becomes equal to q is nothing but 5 milli. So 5 into 10 power minus 3 into what is E bar? Because of sheet charge, the formula is given by rho s divided by 2 epsilon magnitude. Okay, magnitude part we don't bother now. Now direction is also given. So this is a very good question. Where is the charge placed? The charge is placed at origin. Okay, charge is placed at origin. Origin is less than 2 or greater than 2. When you take the point origin, at origin y becomes equal to how much? 0. Is it not less than 2? Yes. So when you take less than, direction is minus. When you take greater than, the direction is plus. That is the logic. Okay. So direction is now minus y cap. Okay, minus y cap. Since the point of interest is placed at y less than 2. Okay, in the sense that below the sheet, kind of y equal to 2 is nothing but the flat surface. Let's assume y equal to 0 is basically below the sheet given to us, and hence minus y cap is what you are taking. Okay, so because of this, the sign minus y cap. Had it been, let's assume, instead of origin, we have been told that point is 0, 4, 0. Means y in that case is nothing but 4. 4 is greater than 2. So then you will take plus y cap here. Okay. Yeah. Now, rest all data we already have. 5 into 10 power minus 3. What is the value of rho s? Rho s is equal to 4 nano. So 4 into 10 power minus 9 divided by 2 into epsilon naught is 10 power minus 9 by 36 pi. Direction is minus y cap. Okay. So we can do the cancellations here. Minus 9 is gone. So 2 cancels out, 4 2 times. So 5 into 2 is nothing but 10. If you take this to the numerator, we'll get 36 into 10. 36 into 10 is nothing but 360. Yeah, so this becomes equal to 360 pi into 10 power minus 3, direction is minus y cap. Okay. So if you do the calculation, 36 into pi means almost 1, right? So this is 1 point something, 1000 into 10 power minus 3 is nearly 1 point something, 1 point something. So I don't think you have an answer here in this data. This rho is, yeah, I think. Please verify if I have done the calculations correct. I don't think there are any mistakes in the calculation. Okay, they have given everything in terms of pi only, no? So I think 0.36, yeah, 0.36 pi. So this is minus 0.36 pi y cap. All the options were given in terms of multiples of pi only. Yeah, good. Let us go to the next question now. Yeah. Two electric charges Q1 minus 2Q are placed at 2 points in space 0, 0, 6, 0. Yeah, 6, 0. And the equation of zero equipotential surface. So this part is very important. You are supposed to find out now the equation of zero equipotential surface. So zero equipotential surface equation you are supposed to find. Okay, so again, what is the logic in this question? All you have to do is nothing but take a random point in space. The point is nothing but x comma y. Okay, and examiner told you that boss potential at point P is nothing but 0. But at that particular point, how many charges are producing potentials? 2 charges. So now we can write this as nothing but Vp1 plus Vp2. Both are added to 0. Potential at point P because of charge Q1, because of charge Q2, both are adding to 0. Okay. What is Vp1? This is nothing but Q1 divided by 4 pi epsilon times R1, and Vp2 is nothing but Q2 divided by 4 pi epsilon times R2. Now that becomes equal to 0. So since it is 0, 1 by 4 pi epsilon is gone. So these two guys are gone. So ultimately, we have right now Q1 by R1, Q2 by R2. That addition goes to 0. What is Q1? Q1 is given as small q. So small q divided by, it is placed at 0, 0. So distance between 0, 0 and x, y becomes how much? That is the square root of x square plus y square. Second charge Q2 is how much? Q2 is minus 2q. Minus 2q divided by square root of distance between this charge as well as the point of interest x, y would be how much? X minus 6 whole square. So this is x minus 6 whole square plus y minus 0 whole square. Okay. So this is what you have, and this adds up to what value? 0. So Q1, Q is gone here again, and we have overall, send this to the other side, square on both sides, we get 1 by x square plus y square becomes equal to, there 2 square is nothing but 4 divided by x minus 6 whole square plus y square. Okay, so we have finally x square minus 12x plus 36 plus y square becomes equal to, on the other side you are having 4x square plus 4y square. This is unfortunately okay, the content is basically, can you hear me? Please let me know if you can. Yeah, unfortunately the content is lost, but anyway I'll get it back to you, don't worry. So we have to redo the problem. I'll just do it a bit fast here since you already came to know what is the logic. There is a point in space x, y. So at that point potential is nothing but 0. Okay, so means that potential because of charge q1, potential because of charge q2, both adds up to 0. And what is the value of Vp1? This is nothing but q1 divided by 4 pi epsilon times r1, q2 divided by 4 pi epsilon times r2. Both adds up to 0. So means 4 pi epsilon times are gone. So finally what we have is q1. q1 is nothing but q divided by okay. So this is where we were. This is where we were. And finally now we can say 3x square plus 3y square, okay, minus 12x plus 36 becomes 0 after you rearrange the terms. You are sending them to the other side. So this is 12 and minus 36. So this is the equation. Okay, this is the equation. So if you see here, I can divide the entire term with 3. So we get x square plus y square plus 4x minus 12. Minus 12 becomes 0. So means I can write this guy as nothing but x plus 4 whole square. So this is, sorry, x plus 2 whole square is what I can write. So means I'll have 4. So I also have to subtract 4. Okay. So if I do that, plus y square minus 12 minus 4 after subtraction is nothing but 16. So becomes equal to, I can say, 4 square. So this is what you have. If you look at the options, x plus 2 whole square plus y square is equal to 4 square, which is nothing but 16. So this is the correct answer. Okay. Yeah, good, Rohan. Nice. So this question also, if you notice, what is the logic? Try to understand the core point here. The core point in this problem is nothing but potential due to a point charge. Potential due to a point charge is simply given by q by 4 pi epsilon times r. So that's it. The moment you understand this formula, no, getting the answer here is not a big deal. Okay. Yeah. Next. This is again another important topic. Usually this is a question that we get in state exams, IES exam, and also once in a while in GATE exam. Okay, in the most recent GATE paper also we have, one of the recent GATE papers also we have got this question. So what is the work done in moving a charge from one point to another point? So here you are having two charges. Let me call the moving charge as nothing but small q. Okay, so whenever you are moving a charge small q, how much is the work done? That is given by q into V2 minus V1, where V2 is nothing but potential at the final point and V1 is nothing but potential at the initial point. So this one, no, we can also write it as, this is also basically equal to q into V final minus V initial. Okay, V final minus V initial. Okay, next, let's assume now you are moving a charge in the presence of some other charge. So here in the second scenario we are having one charge called as moving charge. Small q is nothing but, let's assume, moving charge, and there is one more fixed charge, and that fixed charge is nothing but capital Q charge. So this is basically fixed charge. So in this case, what is the formula for potential? Okay, or what is the formula for work done? Work done expression is given by, there are two ways of noting this. Let's assume this is a capital Q charge. This is not moving. This is not moving. Whereas the small q charge initially, let's assume, is present here. This is a small q charge initial location, and maybe you are moving it through some random path. I don't care what path you have taken, and finally this is where q has reached. Okay, so this is nothing but f. So all I bother about is nothing but distance between the charges. at the final point, this is nothing but RF. Distance between the charges at the initial point, this is nothing but Ri. So this is the moving charge, a charge is moving and finally it went from I to F. So in this case, what is the expression for potential? That is given by this formula, capital Q small q divided by 4 pi epsilon times 1 by R2 minus 1 by R1, where 1 by R2 is nothing but 1 by distance between the charges in the final point of, or this is nothing but in this notation 2. So this is basically 2, this is 1, okay. So this Ri is also called as R1, R2 is also known as Rf. One more formula you have to notice here, that is nothing but potential energy in a two charge system. Potential energy in a two charge system. Okay, so let's assume those two charges are nothing but capital Q comma small q. So let's assume you are having two charges capital Q small q, and how much is the potential energy you have in that system? So this becomes equal to capital Q small q divided by 4 pi epsilon times R. Now by using that formula, we can also understand that this is same as potential energy at the final point minus potential energy at the initial point. So this work done is the extra work that is applied in order to increase the potential energy from initial value to final value, because capital Q small q divided by 4 pi epsilon R2 is the potential energy of final, capital Q small q divided by 4 pi epsilon times R1 is nothing but potential energy initial, and that difference is nothing but the work that you are doing in order to move the charge from one point to another point. Okay, yeah. Next, so let us take this question. This is a question that was given to you in 2021 electrical paper. One more question though, simple question. So there is a 1 microcoulomb charge held at origin. So the charge that is present at origin is nothing but the fixed charge. In our language, this is nothing but capital Q. And if the second point charge, which is 10 microcoulomb charge, which is small q, is moved from, this is the initial point. Okay, please notice, this point that you see is nothing but initial point, and move to a point which is nothing but 555, I can call it as nothing but intermediate point, and finally to 5, 0, 0. So this is the final point. So then how much is the work done? Okay, here please understand, do I care about the intermediate points? No, no matter how many intermediate points we are having, they are of no use for us. We only care about the first initial point and the last final point, that's it. Any number of intermediate points in this case are useless for us, okay, are of no use for us. They are given only just to confuse us, just to waste our time, okay. So in this case, the work done is given by, this is equal to capital Q small q divided by 4 pi epsilon, okay, into 1 by Rf minus 1 by Ri. What is Rf and Ri? Rf and Ri are nothing but distance between the charges at the final point of small q charge, that is the final point of small q charge, and at the initial location of the small q charge. The fixed charge is always fixed. Where is it? Origin. Origin means what? This is basically at 0, 0, 0 all the time. So what is Ri and what is Rf? Ri becomes equal to square root of distance between the small q charge and the capital Q charge. And how much is this distance? This is 0 square plus 10 square plus 0 square, which makes the value of Ri to be equal to 10. And then similarly, what is Rf? Rf becomes equal to square root of distance between the small q charge as well as capital Q charge at the final location of small q charge, which becomes equal to, this is 500, 5 square plus 0 square plus 0 square becomes equal to 5. So I got Rf as nothing but 5, Ri as nothing but 10. So substitute the values, okay. 1 by 4 pi epsilon naught, 9 into 10 power 9, capital Q into small q, capital Q is nothing but 1 micro, this is 10 micro. So 10 total multiplication into micro is 10 power minus 12, okay, into, now here 1 by Rf, 1 by 5, Rf is nothing but 5, Ri is nothing but 10. when you take the LCM here, 10 minus 5 by 5 into 10, 5 by 50 is nothing but 1 by 10. Okay. So overall, when you do the calculation, you get the answer as 9 into 10 power 9, 10 power minus 12 is nothing but 10 power minus 3, 10, and here this is 1 by 10, both are cancelled out in terms of joules. Okay, you got the answer as nothing but 9 into 10 power minus 3, and you have to express the answer in terms of millijoules, and in terms of millijoules the answer is 9. Okay, so this is overall 9 millijoules, right? Yeah. Done. Let's go for the next one. Yeah, this was one of the very good questions, very good previous questions that was asked in EC paper in 2016, if I'm not wrong, 2016 EC branch paper. I think it's year 2017. Okay, and a very good question. Slightly you can say this is on the tougher note side, because the idea won't click for you in the beginning only. Okay, the idea won't click for you in the beginning. Hence, I would put this in the category of tough question. But yeah, conceptually good question this is. Okay, conceptually good question. So what happens is nothing but there is electron, which is the first charge Q1. This is a moving charge. Okay, this guy is moving in free space with a velocity of 10 power 5 meters per second towards a stationary electron. There is another electron right now, or another charge Q2 far away. So there is Q1. So this is Q1, and far away you are having Q2. Okay, Q2. This is another electron. This is not moving, this is moving. Okay, so this is a moving charge. So this is moving, and approaching the stationary charge. Obviously, since both are electrons, what kind of force they will have? They will have some kind of repulsive force. So the first electron is traveling towards the second charge. Okay, and yeah, the opposition is increasing because the distance is decreasing between both the charges. So at some point of time, the opposition will be very large that the charge Q1 has to stop. And after experiencing a lot of repulsive force, now it will start moving backward. Okay, so now the examiner told you the closest distance that the moving charge gets to the stationary electron is dash. Okay, so like I've told, it moves, and whenever it moves, since it is experiencing repulsive force, the velocity decreases, and at some point of time, the velocity becomes equal to 0. Okay, so yeah, maybe here the velocity is nothing but 10 power 5. It was given as 10 power 5 meters per second, right? Maybe at some distance, the velocity decreases. Maybe, let's say this point, we are having a random point I've taken. Velocity becomes 10 power 4 meters per second. So velocity decreases by almost 10 times. Okay, and so on. Okay, at some point, what happens is nothing but your Q1 reached this location. Okay, so at this location, velocity becomes 0. Okay, velocity becomes 0. So whenever this velocity becomes 0, now you have to say how much is the distance between both of these charges. Okay, so this is the main goal here. Okay, yeah, in the first case the distance was not given. Only thing is, it was told to us that the point is nothing but far away. Far away means at the initial location. This is nothing but the initial location. Okay, and this is nothing but the final location of Q1. Yeah, and after that again what will happen? Q1 will, because of repulsive force, Q1 will move back towards its original location only. Okay, so at the initial location, how much is the distance between the charges? Since it's a faraway point, I can say that Ri becomes equal to infinity. So this simply becomes equal to infinity, right? Yeah. So this becomes equal to infinity. Distance is very large. Okay. So because of that, potential energy at the initial location becomes how much? This is nothing but capital Q small q, or in this case Q1 Q2 divided by 4 pi epsilon times Ri. So Ri value is nothing but infinity, distance is very large, and in such a way that the potential energy becomes equal to 0. Where? At the initial point. Okay, but what do we have at the initial point? We have kinetic energy. So kinetic energy at the initial point becomes how much? It's a non-zero value. How much is the value? Half mv square, where velocity is nothing but 10 power 5. We have this information. At the final point, velocity is 0. So when velocity is 0, what is kinetic energy at the final point? At the final point, how much is the kinetic energy? Yeah, I can say ki half mv square becomes equal to 0, right? There is no kinetic energy, velocity is 0. But what is the potential energy at the final point? This becomes equal to capital Q small q divided by 4 pi epsilon times d. Because the distance between the charges now is a finite value, it's not an infinite value. So due to that, yeah, this value is a non-zero value right now. Now we all know that law of conservation of energy always applicable. So since law of conservation of energy is always applicable, here how much is the total energy? 0 plus half mv square becomes equal to, here how much is the total energy? 0 plus capital Q small q divided by 4 pi epsilon times q or d, and equate both of them. This system that we have taken is a lossless system, right? So there shouldn't be any energy losses here. So because of that, the total energy in the initial case and the total energy in the final case both should become exactly one and the same. Okay, so that is what you are supposed to do. So finally, what happens is nothing but for total energy initial becomes equal to total energy final. Okay, and whenever you substitute the data here, potential energy initial plus kinetic energy initial, this should become equal to potential energy final plus kinetic energy final. That's it. So how much is the potential energy in the initial case? We have seen distance is infinity and hence potential energy is 0. So in the beginning, the total potential energy is nothing but 0. All we have is only kinetic energy, which is half mv square. And in the final case, how much is the potential energy? We have seen capital Q small q divided by 4 pi epsilon times d. D is unknown value. And how much is the kinetic energy final? 0. Because the velocity of that particular electron has become 0. So yeah, we have taken kinetic energy 0. Okay, in this case, capital Q small q is nothing but basically q square only. Now let us substitute all the values. Half mass of electron is given to you. Mass of electron is basically 9.11 into 10 power minus 31. So 9.11 into 10 power minus 31 into V is 10 power 5. So 10 power 5 whole square this is. RHS 1 by 4 pi epsilon becomes how much? This is 9 into 10 power 9. Q1, Q2, both are same charges, both are electrons only. What is the charge of electron given? 1.6 into 10 power minus 19 square. So 1.6 into 10 power minus 19 square. So I don't care plus or minus because anyway we are squaring. And denominator is nothing but d value. Denominator is d. Yeah, that's it. This is the calculation ultimately. All you have to find out is nothing but d. So please do it. Ten power 10, 10 power 31, 10 power minus 21. 10 power minus 19 square is 10 power minus 38. And 10 power 9. Both combined we are having 10 power minus 38 plus 9 minus 29. So this is 10 power minus 29. Okay. So then finally d becomes equal to, now basis of this, d becomes equal to, d is equal to 2 into 9 is 18 into 1.6 square is 2.56 into 10 power minus 29 divided by, this is 9.11 into 10 power minus 21. Okay, and I think you have to answer in terms of 10 power minus 8. Okay, Okay, you have to express everything in terms of 10 power minus 8, which is what is this guy, I believe, right? This is 10 power minus 8 only. Yes. Then the remaining calculation you have is a very simple calculation now, the remaining calculation, which is 18 times 2.56, 9.11. So 5.05. So the distance between them becomes equal to 5.05 into 10 power minus 8 meters. So this is the closest distance between the charges. So here what is the concept? The concept is nothing but potential energy in case of a two charge system. The formula is nothing but capital Q small q divided by 4 pi epsilon times r, and the remaining part is basically law of conservation of energy, which is pretty much trivial. Okay, pretty much trivial. Yeah, please answer this question now. Yeah, please answer this question. So again, we are supposed to find out the work done in moving a charge from one point to another point. What is the formula? The logic here is nothing but approach. If you remember the approach, the task is done. So work done becomes equal to here Q into V final minus V initial. That's it. So you have to calculate the expression for potential. I have expression for electric field intensity. Can you calculate expression for potential by using electric field intensity? Yes. We have the logic as nothing but what? What is V? V is equal to minus integration of E dot dl. But the given data is in terms of what coordinate system? Spherical coordinate system. In spherical coordinate system, what is dl bar? I have E bar anyway, but what is dl bar in case of spherical coordinate system? This is dr times r cap plus r d theta times theta cap. And I don't even bother about phi cap because there is no phi cap term here, so we don't even have to write the phi cap term here. So when you take the dot product, so what is the expression we get now? This becomes equal to integration of with a minus sign. So integration of r dr. Anyway, I'll write the expressions. 8 r sine theta dr. First one. The second one is minus sign is common here. This is 4r. We have cos theta. Again r, one more r is there. So 4r square cos theta d theta. Okay, so this is what you have. So when you integrate, what do we get? Minus term common. There are two integrations right now. The first integration is nothing but 8r square sine theta by 2, which is nothing but 4r square sine theta is the first one. What about the second one? The second one is nothing but 4r square integration of cos theta is nothing but sine theta. So this is 4r square sine theta. Yeah, anyone tell me what is the answer? Correct answer? What is the expression for potential here? Correct answer for potential is what? What is the correct answer for potential here? What is the correct answer for potential? What is the correct answer for potential? I don't want number, I want, is that the correct expression or, yeah, good, nice Pavani. So duplicate terms, remove them. So whenever you have a duplicate term, you have to remove it. Be cautious about that particular statement, mainly in terms of line integrations, not just in electric fields, but rather whenever you are performing line integrations, that concept is always applicable. Wherever you see duplicate term, remove the duplicate terms, okay? So finally, we have got the expression for potential as nothing but V becomes equal to now minus, this is only minus 4r square sine theta, okay, sine theta. So on the basis of this, what is V initial? V initial. What is the initial point? Initial point is nothing but A. From initial point, this is the starting point, VA becomes equal to minus 4 into, this is nothing but R is equal to 10, so 10 square into sine pi by 6, okay. And how much will be this answer? 400, sine pi by 6 is sine 30, sine 30 is half, so 400 by 2 is 200, so this is minus 200 volts. And what is V final now? V final is equal to minus 4 into, at the final point again, yeah, this is 10 square only, into sine of pi by 2. Sine pi by 2 is how much? 1. So this is minus 400 volts. Minus 400 volts, right? So when you substitute these two values here, finally, finally the answer becomes equal to now. This becomes equal to, what is the charge? Charge is minus 5 micro. So this is equal to minus 5 into 10 power minus 6 into Vf. Vf is equal to minus 400, minus of minus is plus 200. So you get minus 200 here, minus 200 into minus 5 is nothing but 1000. 1000 into 10 power minus 6 is 10 power minus 3 joules, which is also obviously equal to how much? 1 millijoule, okay. But here again the underlying concept is what? The work done, there are two concepts here. Work done in moving a charge is nothing but Q into V final minus V initial, the first point. Second point is nothing but, yeah, how do you get expression for V from E? V is equal to minus integration of E dot dl, okay. So both of this we have to use to get the final answer as nothing but, in this case the total work done is nothing but 1 millijoule. Clear? Yeah, good, Rohan. So next is nothing but conservative nature or irrotational nature of only electrostatic fields, okay. So this nature is only there for electrostatic field, and the proof for this is very simple, not a tough proof. So earlier we have got the expression for electric field intensity, right? E bar. What is E bar equal to? Negative of gradient of V. So what I am doing right now is nothing but I am taking curl on both sides. When you take curl on both sides, we get here del cross E bar LHS. RHS, what we are having? This is minus of gradient of, curl of gradient of V, right? And in double differentials, there are two important rules. The two important rules are nothing but divergence of curl of any vector field is always 0. Curl of gradient of any scalar field is always 0. No matter what, is always 0. Okay. So here we have curl of gradient of any scalar function, no matter what you take, is always 0. Or to be more precise, null vector always is nothing but null vector. Okay. And hence what we have is nothing but, now we have a curl of electric field intensity is nothing but 0. Okay. So due to which we are calling electric field intensity, we all know that whenever any vector field curl is nothing but 0, that field is known as basically conservative field or irrotational field. Irrotational means what? The field does not have the ability to cause circulation, okay, to cause rotation, and hence we are calling it as nothing but irrotational field. So in case of irrotational field, always remember 4 points. I have written 3 points here. The first is nothing but curl of the field is always 0. Second is nothing but closed path integration is 0 irrespective of path of integration. This is very important. Not on a specific path, irrespective of the path, closed path integration for only conservative and irrotational fields is nothing but 0. Okay. And the next one is nothing but open path integration. So next is nothing but open path integral is independent of path of integration. It only depends on the initial as well as final points, but not on path of integration. No matter what path you take, okay, as long as the initial and final points remain same. Please notice these are line integrations. These are line integrations. So this is open path integration. First case L1, second case L2. But in both cases you are going from where to where? I to F only. Okay. And the result of that particular open path integration is independent of path of integration, but only depends on the initial as well as final points. In both of these cases, initial and final points are same. Okay. And hence the result of integration remains exactly the same. Okay. Yeah. And the last one more point, the fourth point I've told you is nothing but, the fourth point is, okay, there always exists there always exists a scalar potential that defines E bar as, basically we all know that E bar becomes equal to minus gradient of the static potential, which is nothing but V. In fact, that is where we started with. So we are saying that for every electrostatic potential E bar, there exists a scalar potential called as V. Okay, and how both of them are defined? By means of this relation. Okay, so these are the 4 points which are true not just for electric fields but rather for any conservative field. No matter what conservative field you take, these 4 points are always true. Okay, so from now on, understand that whenever we have electrostatic field is always conservative, and hence the curl of the field should always become equal to 0. Okay. Yeah. This is a more recent GATE question. It was a 1 mark question, 2024. We have been given two vector fields, F1 as well as F2. F2 looks familiar to us, minus y x cap plus x y cap with a minus sign. If you take minus sign common, we'll get inside minus y x cap plus x y cap, that kind of a field. So we are supposed to tell which of them are electrostatic here. Okay, only one F1 is electrostatic, only F2 electrostatic, both neither. This is what you are supposed to do. So what is the logic here? All you have to do is nothing but take curl, and if it is 0, yes, it is electrostatic. If it is not 0, not electrostatic. Okay, so let me calculate the curl of the first one. Curl of F1 first of all becomes equal to how much now? X cap, y cap, z cap by 2x. Yeah, so we have A is anyway common. Excuse me. The x component is nothing but y, and y component is x. This is 0. Okay, so this becomes equal to x cap. Dou by dou y of 0 is 0. Dou by dou z of x is also 0. Minus y cap. Dou by dou x of 0 is 0. Dou by dou z of y is again 0. Plus z cap. Dou by dou x of x is 1. Dou by dou y of y is again 1. 1 minus 1. So all you got is nothing but what? Everything is 0. So 0 x cap, 0 y cap, 0 z cap. So total we have got 0 bar, which is null vector. Okay, which is null vector. So we have got del cross F1 to be equal to 0. So on the basis of this, we can say F bar is electrostatic. F bar is electrostatic. Okay. So now similar thing we are supposed to do it for F2 also. So again, I'm supposed to take one more curl. Okay, I want you guys to verify the second one. Okay, I'll give you the answer directly. The second one, del cross F2. When you do this curl calculation, you get the answer as nothing but minus 2. You are having coefficient as nothing but a here, minus 2a. Direction would be z cap. Okay, so this is the answer you get if you do the calculation. Means what? This value first of all is not 0, right? This is not a null vector. This is not null vector. Means what? F2 is not electrostatic. So on the basis of this, F2 is not electrostatic. Okay. So as per the given options, only F1 is electrostatic, F2 is not electrostatic. Simple question if you notice, which is a question of statics, but rather asked in EC paper. So EC students, they only focus on transmission lines, EM waves, antennas, waveguides, but rather they neglect these easy topics. Okay, so these easy topics will give you, some decent marks. Okay. Yeah. Next, previously, in order to prove that the electric field is nothing but conservative, we have taken curl for electric field expression. Now all you have to take is divergence. Okay, so E bar becomes equal to how much? Minus gradient of V. That is how we have started earlier also in conservative fields discussion. Here E bar is equal to minus gradient of V, and then we have taken curl. Now what you do is nothing but take divergence. Okay, so in this case now take divergence. When you take divergence, this becomes equal to del dot E. Yes, RHS, what do we get? RHS is nothing but divergence of gradient of V. What is divergence of gradient? Divergence of gradient is also called as Laplacian. So RHS now will be called as Laplacian. This is basically Laplacian with a minus sign though. Here, what is this guy? Del dot E. Is it not our Maxwell's first equation? Yes. This is Maxwell's equation number 1. And from that, this becomes equal to rho v by epsilon. And what is the expression of Laplacian? Laplacian is nothing but del square the function. There is a minus sign and hence obviously minus sign. Okay. And when you rearrange the terms, finally what you get is nothing but del square v becomes equal to minus rho v by epsilon. This becomes equal to minus rho v by epsilon, which is our Poisson's equation. This is the first one, Poisson's equation. And when you take source free region, when the region given to you is nothing but source free. Source free means what? The region is free of sources of electric field, which is basically charges. Okay. So source free region, one more name is nothing but charge free region. So when you take a charge free region, in that case, yeah, rho v becomes 0 and hence del square v becomes also equal to 0. And what is the Laplace equation? Laplace equation is nothing but a second order partial differential equation. And solving this Laplace equation by using the boundary values of v is known as boundary value problems, not boundary conditions but rather boundary value problems. Okay. We have got only one question on boundary value problems, that too in GATE 2022 if I am not wrong. Okay. Yeah, this is a GATE question, a recent GATE question. In a source free region, the most important wording in this question is nothing but this statement that, yeah, now you are having a source free region. So whenever we have source free region, what happens? Rho v becomes equal to 0. So when rho v becomes 0, so in this case, what is del square Laplacian of, what is the Laplacian of the scalar function or Laplacian of potential function becomes how much? 0. I have been given scalar function there, and now what I have to do is nothing but I have to take Laplacian of that. What is the Laplacian formula? In case of rectangular coordinate system, this is dou square v by dou x square, dou square v by dou y square, dou square v by dou z square, and this should become equal to 0. In the given scenario, if you take first differentials, don't take it a double differential directly. Sometimes you may do some mistakes. What is the first differential with respect to x? Dou v by dou x. This is basically v. Dou v by dou x becomes how much? 4x. Dou v by dou y becomes how much? 2y. And dou v by dou z becomes how much? This is 2cz. Differentiate this dou v by dou x with respect to x, again we get 4. Differentiate this 2y with respect to y, again we get 2. And differentiate 2cz with respect to z, again we get 2c. Okay. And this should become equal to 0. And finally what do we have? 6 plus 2c is nothing but 0. So c becomes equal to minus 3. Okay. So c is minus 3. We got the answer. Okay. Simple question only, if you notice. All you have to notice nothing but, yeah, there is something called as Poisson's equation. But Poisson's equation, Laplace equation, conservative nature of electric field, what is the basis for all this? The basis for all this is nothing but this expression that electric field intensity is equal to negative of gradient of V. The moment you remember this, take curl, you will get conservative nature of electric field. Take divergence, you get yeah, this Poisson's as well as Laplace equation. Okay. Yeah, good. Minus 3. Good, nice. Let us proceed further. Another important topic in electrostatics, where you get a lot of questions, is spherical shell or spherical conductor, metallic conductor, hollow metallic conductor. They use various notations, but in all these cases, yeah, the name that I generally use is nothing but spherical shell problems. So here you are having a spherical shell whose radius is nothing but some a. This is a shell. Okay, radius of this shell is nothing but a. Charges are present only on the surface. So whenever you take a shell or you take a spherical conductor, doesn't matter what, in all these cases what happens? Yeah, in all these cases what happens is nothing but, okay, charge exists only on the surface. So charge exists only on the surface. So due to which, whenever you take electric field inside, so I'm taking now 2 points. One is nothing but inside and one more is outside here. So when you take R less than A, so here R is less than A, and hence we are calling it as nothing but inside region. Inside, are we having any charge? No, there is no charge. Since there is no charge, electric field becomes 0. But on the outside, do we have charge? Yes. So here, this is the region of R greater than A outside. Okay. So spherical shell for the outside region behaves the same as compared to point charge. Okay, behaves the same as compared to point charge. If you notice here, outside scenario, what is the potential? Same as point charge. What is the expression of electric field? Again, same as point charge. Point charge, what is the potential? Okay, point charge potential is Q by 4 pi epsilon R. And outside, what is the electric field intensity? Q by 4 pi epsilon times R square. Yeah, both of them are basically same as point charge scenario. Okay, but inside, the situation is different. Inside, the electric field is nothing but 0 because there is no charge, but potential is nothing but constant. Here we are taking A is nothing but the radius of this particular shell. So due to which the potential inside, okay, so the potential inside is also equal to potential on the surface. Potential on the surface. And this is basically a constant value. It does not change inside, it only changes on the outside. Outside, how do they change? They decrease. When you are going away from the shell, electric field intensity decreases, potential also obviously will naturally decrease because V is proportional to 1 by R outside, E is proportional to 1 by R square outside. So electric field outside decreases with R, potential also decreases with R, and inside electric field is 0. Potential is constant, potential is not constant but not 0. Understand? The value is not 0. Okay, it's a constant value though, but rather it's not 0. So this is for spherical shell. Let's look at a few problems now. Again, electrical 14. Okay, not so old question, pretty, I find a pretty recent question also, but rather decently recent question. A hollow metallic sphere of radius R is kept at a potential of 1 volt. So means, what is this 1 volt? Can I say this is potential on the surface? Yes, this is basically potential on the surface. Okay, so I can say that 1 volt becomes equal to Q divided by 4 pi epsilon times A, where A is nothing but radius of the shell. In this case, radius of the shell is nothing but small r. As per the given data, this A is nothing but radius of the shell. Radius is given as, in this case, small r. Okay, so hence I can write the expression for Q now. In this case, Q becomes equal to 4 pi epsilon times into 1, no? So means 4 pi epsilon times small r. So this is the value of small q. Okay. Now what were you asked? The total electric flux coming out of the concentric spherical shell of surface radius r greater than small r. So r greater than small r means what? We are outside or inside? We are outside. So now if I ask you, I want to calculate the total electric flux, phi E out of S becomes equal to how much? Charge enclosed by a closed surfaces. So inside the closed surface, how much is the total charge we have? Just now we have calculated this value. So this is the total charge we have on top of the shell, and that becomes equal to 4 pi epsilon times r. That's it. So this is the total flux coming out of S. What is the logic here again? Gauss law. So we have used Gauss law as well as also the potential due to a spherical shell. So finally the answer is 4 pi epsilon times r, small r. Not capital R we are supposed to take, small r is what you are supposed to take, because small r is the radius of the shell given to you. Accordingly you are supposed to take small r but not capital R. Okay. Again, the spherical shell is one very important topic from where you can get questions. right? Yeah, solve this question right now. A thin soap bubble of radius r, which is equal to 1 centimeter and thickness some 3.3 micrometer, is at a potential of 1 volt. So this is a thin soap bubble. Thickness is given as r. So it's not the entire shell also. So only here, up till here we have diagram was not proper here. Yeah, so we have a small thickness only here. So this thickness, so this was originally our soap bubble. Okay. So this soap bubble now is burst into a small drop, so which became a solid sphere right now. And the potential is equal to 1 volt with respect to reference point at infinity. And the thickness is given as 0.33, and the radius of the bubble is given as 1 centimeter. Okay. Yeah. So here, do you know the radius value? No, we don't know the radius value. But can I say that when soap bubble bursts and becomes a solid soap drop, volume remains same? Yes. So volume V1 becomes equal to V2, where in this case V means volume, physical volume of the soap bubble remains same. So means what is the volume in the first case? Sphere there, this is solid sphere, that is hollow sphere. What is the volume of that hollow sphere having a very small thickness? That is nothing but 4 pi radius square here. What is the radius of the first bubble? Capital R. So 4 pi capital R square, okay, times the thickness. How much is the thickness? Thickness is nothing but A. So this becomes equal to the volume of this soap drop. This is a solid sphere. For this solid sphere, how much is the volume? 4 by 3 pi unknown value of R whole cube. So means indirectly the examiner also gave you the value of small r. Indirectly, not directly though, indirectly. Okay, so they want us to calculate this. 4 pi and 4 pi is gone. And I can say that, here r cube becomes equal to, this is 3a r square, 3a r square, and finally what is r equal to? 3a r square whole power 1 by 3. So this is the value of small r. So a is known to us, a is equal to 3.3 micro and r is nothing but 1 centimeter. And if I substitute the data there, you will get your answer. In fact, let's do the calculation also. What's the big deal? So 3 into 3.3. How much this is? 9.9 micro. Micro means 10 power minus 6 into r square. R is equal to 1 centimeter. 1 centimeter is 10 power minus 2 meters. Whole square is 10 power minus 4. So this is 10 power minus 4. Okay. Whole power 1 by 3. 9.9 is approximately equal to 10. 10 power minus 10 into 10 becomes equal to 10 power minus 9. Whole power 1 by 3 becomes equal to nearly, this is 10 power minus 3 meters. Okay. So this is the value of small r. I got the value of small r. Now what we are supposed to calculate? The volume of soap bubble. Yeah, they have given the data also nicely for us. They have given this data also. The potential in volt of the resulting single spherical drop with respect to the same reference point at infinity is dash. Okay, so we have to calculate now potential of this guy. Again, whenever the soap bursts, do you think charge will change? No. So the total charge in the first and second case remains exactly the same. Okay. So whenever we have a small bubble here, what is the potential formula? Potential in the small bubble or potential in the soap drop. This is soap drop, this is soap bubble. So potential of soap drop basically now becomes equal to Q divided by 4 pi epsilon times the radius of this drop. The radius of this drop is nothing but small r. Do you have the information of radius of the drop? Unfortunately, now yes. But rather, do you have the information of charge? No. Charge information I don't have. Okay. So how do you calculate the charge information? By using this value 1 volt. Okay. What is the potential of soap bubble? Okay, the potential of soap bubble is given to us as nothing but 1 volt. But what is the formula? The formula is nothing but Q divided by 4 pi epsilon times radius. Okay, whose radius? Radius of this particular bubble, which is nothing but 1 centimeters, which is capital R. So this is capital R, right? But like I've told, in both cases, the value of Q remains same. So since value of Q remains same, I can say that the ratio of soap drop potential, okay, divided by potential of soap bubble, now becomes equal to how much? This becomes equal to, in both cases, 4 pi epsilon are cancelled out, Q and Q are also cancelled out. All you have is nothing but, this is 1 by R, and there you are having soap bubble 1 by capital R. So which becomes equal to capital R by small r. And how much is that ratio? Capital R is equal to 1 centimeter 10 power minus 2, and small r we have just now calculated this to be equal to 10 power minus 3. So this is 10 power minus 3. Okay. So when you do the calculation, we get capital R. So how much is the total value? I think 10, right? So this becomes equal to 10. Okay. Yeah. And what is the value of soap bubble? So bubble potential we know. So this is nothing but 1 volt. So on the basis of this, what is the potential of soap drop? Soap drop potential becomes equal to 1 here, 10 there. So total 10 volts. That's it. Okay. So if you are, pretty comfortable with numbers and calculations, no? So we don't even have to use calculator for solving this question. Okay. The data was deliberately given to you in such a way that, yeah, you are getting round figure numbers. Okay, which is nothing but in this previous case, 3 into A, 3 into 3.3 is 9.9, which can be nicely approximated as 10. For this also you can use calculator. There is nothing wrong, but rather it would take a lot of time for you. Ultimately, there also whatever answer you get is almost equal to 10 power minus 3 meters only. Okay. This is again another very good question that you have in the previous years. Again, the previous years, right? So I hope this part is complete. So I think this is the last topic we have in case of electrostatics. So again, we will take a small break, not a lengthy break also, 15 minutes break. It's right now 6:30, 6:45 we'll be back. Okay, 6:45. Okay. Thank you. Okay. So welcome back. Okay. Next we'll start with magnetostatics revision. So again, just like electrostatics, here in magnetostatics we have basically 4 components, 4 terms. The first is intensity term, which measures the strength of magnetic field, and the units of magnetic field intensity is nothing but amperes per meter. There it was volts per meter, but here it is nothing but amperes per meter, right? Okay. And next we have magnetic flux. Magnetic flux is the total number of flux lines crossing a given surface, just like electric flux. And the units for this is basically Webers. Webers is the MKS unit. There is also another unit which is Maxwell. Okay, Maxwell is also the units of magnetic flux. Next we have flux density, which is the number of flux lines crossing a given unit area, having the units of Webers per meter square, which is also basically Tesla. Okay, also known as Tesla. And lastly we have vector potential. Magnetic vector potential is a quantity which defines the flux density. Okay, so it defines the flux density having units of Webers per meter. So this is Webers per meter. So these are the 4 quantities. Units is very important to recognize the correct quantity that was given to you. Okay. Next, we have to discuss here mainly about 3 types of current distributions. One is line current, sheet current, and volume current. And whenever line current is given, the total current that is flowing through the conductor is nothing but I only. And in case of sheet current, current is basically flowing along a particular surface or along a sheet. Surface current or sheet current, both are same thing. So in this case, the total current is given by integration of k bar dl. So where here k bar is nothing but current density. So this is known as the sheet current density. Having units of amperes per meter. Okay, having units of amperes per meter. And lastly, we have volume current density. In case of volume current density, current is flowing in a volume but coming out through a surface. Okay, you have to understand that flow is happening in a volume, but rather it is coming out of a particular surface. Okay, and this J bar, which is the volume current density. So this is volume current density. Having units of amperes per meter square. Even in the previous case also, yeah, current is flowing on a surface, but rather it is coming out through a particular line. Okay, flowing through a surface, but rather coming out through a particular line. So that is what you have in case of sheet current scenario. Okay. Next, let's look at this problem. Recent question, 24, GATE 24 question. A wire of circular cross section with a radius of A. So the radius of this particular cross section is given as A. This cross section radius is nothing but A. The current density is given by J is equal to K S square, where K is a constant and S is the radial distance from the axis. So in our language, the distance from the axis is basically called as what? Rho. So even though they have given in their notation, we will convert them into our notation. This is nothing but K times rho square. K times rho square. And if nothing is mentioned, we assume that the flow is happening along the axis, and that axis is nothing but for us Z axis. Okay. And the radial distance of the axis 0 less than x less than A. Basically this is S. This has to be S less than A. The total current that is flowing in the wire is dash. Okay. In case of magnetostatics or in case of volume currents, if nothing is mentioned, you can always safely assume that current is flowing along Z direction. Okay, by default current is always flowing along Z direction. So in this example, this axis corresponds to This axis corresponds to now Z axis. So current is now flowing along Z axis. It will help you identify what is the proper ds bar you are supposed to take. Now I want to find out what is the total current. What is the formula for total current in case of volume current distribution? So this is nothing but integration of j bar dot ds bar. Now what is the ds bar you are supposed to take? Since current density is along z cap direction, ds bar also along z cap direction. What coordinate system we will take? Nicely I can see a cylinder here, means cylindrical coordinate system. So this is integration of k times radial distance square z cap dot. Now along z cap, what is the differential surface area in case of cylindrical coordinate system? This is nothing but rho d rho d phi. Direction is how much? Z cap only. Z dot z is nothing but 1. Rho into rho square is nothing but rho cube. So this is k into integration of rho cube is how much? Rho power 4 by 4. Integration of d phi is how much? Phi. Okay. Now what is the radius? Radius is nothing but a. So means the integration happens from 0 to a. And for phi, the limits are from 0 to 2 pi. Substitute everything. What do we have right now? A power 4. So this is k a power 4 into 2 pi divided by 4. So when you rearrange the terms, finally, what is the answer you get? 2 pi by 4 is nothing but pi by 2. So this is k pi a power 4 by 2. This is the answer. Now look at the options. I think pi k a power 4 by 2, option B. Okay. Straightforward question, nothing great we have here in this question. Yeah, all you have is nothing but total current is nothing but integration of j dot ds. That is the formula. And surprisingly, this was a 2-mark question. Okay, this is actually a question that deserves 1 mark only, but rather this was given for 2 marks. So you have to understand that sometimes luck can be on your side. If you get this question for 2 marks means you should be very happy. Okay, volume is low. Okay. Yeah, next, Ampere's law. Just like Gauss law in case of electrostatics, we have Ampere's law here, and Ampere's law as well as Gauss law, both actually are basically telling you the same story. That is nothing but outcome is equal to source. Okay. So source is equal to outcome is what it says. It says that Ampere's law states that circulation of magnetic field intensity. Circulation of magnetic field intensity is nothing but outcome. Yeah, magnetic field circulates because of what? Because of a source. Who is the source? Current. And that is basically the RHS. Okay. So this is source. Okay. So here integration of h dot dl, which is nothing but basically outcome. So this is outcome, becomes equal to current enclosed, which is nothing but source of magnetic field. This itself is nothing but the source of magnetic field. Okay. So here we have a closed path integration. So since we have a closed path integration, we can apply Stokes theorem. Okay. So this closed path integration that you see, we can use Stokes theorem, and by Stokes theorem we can convert this integral h dot dl by means of integral del cross h dot ds. Okay. RHS, since we are having here surface integration, I am taking RHS also in terms of surface integration format. We have current in terms of surface integration format is nothing but integration of j dot ds, and that's what you have taken. So when you equate both of these integrands, now you have basically the curl of magnetic field intensity being equal to j bar. Okay. So this is basically the Maxwell's equation number 4. Okay. So till now we have seen 3 Maxwell's equations. The first is nothing but divergence of electric field intensity, and divergence of electric field intensity or del dot D, divergence of flux density. Del dot D becomes equal to rho v, first one. Next equation we have seen is Maxwell's equation number 3, and the Maxwell's equation number 3 is curl of electric field. Curl of electric field, since electric field is conservative or electrostatic field is conservative, curl of electric field intensity is nothing but null vector, that is the second one. And the fourth Maxwell's equation in order is nothing but Maxwell's equation number 4 is curl of magnetic field intensity becomes equal to current density, that is producing that particular magnetic field intensity. Okay. Yeah, stronger the source, stronger will be the circulation. Okay, stronger will be the circulation of that particular field. Clear? So this is regarding Ampere's law. Let's look at a few questions on Ampere's law. Again, pretty recent questions these are. 2021 question. The magnetic field intensity H bar is given and the magnitude of current density. So you are supposed to calculate here what? Current density J bar. What was given to you? Magnetic field intensity H bar is given to us. And at a particular point, we have x, y, z. We have here x, y, z being how much? 1, 2, 1. That is what is given. And what is the formula linking both? Current density becomes equal to this is curl of magnetic field intensity by means of Ampere's law. By means of Ampere's law. Okay. Yeah. So let us take the curl of given magnetic field expression. So this is x cap, y cap, z cap, differential terms. And what is the x component? X square. Y component, x square, y square. Z component, x square, y square, z square. Okay. And hence what is x cap term right now? Dou by dou y of this term, which is 2x square y z square minus dou by dou z of this term is 0. Minus second term y cap. Dou by dou x of this term 2x y square z square minus dou by dou z of x square is nothing but 0 plus z cap. Dou by dou x of x square y square is 2x y square minus dou by dou y of x square is nothing but 0. So this becomes equal to 2x square y z square x cap minus y cap into 2x y square z square plus 2x y square z cap. Okay. Now, the point given to us is nothing but 1, 2, 1. So x is 1, y is 2, z is nothing but 1. So when you substitute that, you get x is 1, y is 2, z is 1. So 2 into 2, 4. So this is 4x cap minus y is 2. So 2 square is 4. 4 into 2 is nothing but 8 minus 8 y cap. Y square is nothing but 2 square. So 2 square is 4. 4 into 2 is 8 plus 8 z cap. Okay. And you are supposed to calculate the magnitude, only the magnitude. Obviously, the units is in terms of what? Current density amperes per meter square. And if I want the magnitude of this, the magnitude is nothing but square root of 4. This is 4 square is nothing but 16 plus 64 plus 64. 64 plus 64 is 128 plus 16 is 144. And how much is magnitude now? Magnitude is 12. Okay. So this is nothing but 12. Right? Simple question again. All you have to remember is nothing but Ampere's law. So this is a straightforward question of Ampere's law. Nothing great. Okay. So in 2021, if you see, we have got a question on Gauss law as well as also on Ampere's law. If you remember one of the previous questions that we have solved, in 2021 in electrical paper, we also have a question on Gauss law. So Gauss law, Ampere's law questions are very simple, divergence and curl calculation only, nothing great. Okay. Next, whenever we have volume current distributions, just like volume charge distribution scenarios we had earlier, what is the logic we are supposed to use? Okay. So now also the logic is nothing but I am going in circle whenever I am going in a closed path, because LH is in case of Ampere's law is what? Integration of H dot dl. If H is constant, you can keep it outside, and if you keep this outside, integration of dl becomes how much? Length. So now since you are going in circular path, how much is the length of a circular path? Length of a circular path obviously is the perimeter, which is h into 2 pi l. So what is this? What is this? This is basically the circulation of h bar. Okay. So h into the length of path. Okay. And that becomes equal to how much? What is this guy and what is this guy? This is nothing but current enclosed. Both of them are nothing but current enclosed. What is the difference between both of them? The only difference that you have in both of them is nothing but in terms of the limits, upper limit, that too. For the inside scenario, again rho less than A means what? You are having inside scenario, and rho greater than A means what? You are having outside scenario. Okay. So for inside scenario, you are integrating from 0 to rho, and for outside scenario, you are integrating from 0 to A, where in this entire discussion, A corresponds to how much? A corresponds to radius of the current distribution. So here A corresponds to the radius of the current distribution. Okay. If you understand this logic now, it will greatly help you in saving a lot of time in exam. That is very important. So this was a previous question again, 2022. Again Ampere's law application. 21 also we have got Ampere's law question. 22 also we have got Ampere's law question. So you can notice that this is one topic that you can't miss. Okay. So we have a long conducting cylinder having a radius of B. Here the radius is given as B. Okay, radius is nothing but B. And the current density is given as some function. Current density is given as some function for the region R less than B, where R is nothing but the radial distance. In our language we call it as rho. Okay, rho for us is R according to examiner. So wherever I see rho or wherever I see R, in my mind I will recollect it as nothing but rho only. And the magnetic field intensity H for the region inside the conductor. Okay, so for the region inside the conductor. For the region inside the conductor, what is the Ampere's law application formula? H into 2 pi rho becomes equal to integration of J bar dot ds bar, and the integration happens from where to where? 0 to rho. Okay, 0 to rho. So wherever I see R, I'll write it as nothing but rho terms here, and write the expression. What is the current? Current is nothing but J naught or some J A. R cube means rho cube z cap dot ds bar along z cap direction. What is ds bar in case of cylindrical coordinate system? This is nothing but rho d rho d phi z cap. Z dot z is nothing but 1. So this becomes equal to, and by the way, integration happens from 0 to rho. J A, I can keep it outside. Okay, rho cube into rho is nothing but rho power 4. Integration is rho power 5 by 5. And limits are from where to where? Limits are from 0 to rho only. And integration of d phi is nothing but phi. So since this is a cylindrical conductor, the range of phi is nothing but 360 degrees. So 0 to 2 pi. Okay. So on the basis of this, now I can say H into 2 pi rho LHS becomes equal to RHS is what? JA, this is JA into rho power 5 by 5 into, this is 2 pi. This is 2 pi. So 2 pi as well as 2 pi is gone. Rho cancels out rho power 5, rho power 4 times. So finally H becomes equal to JA rho power 4 by 5. So this is the expression. Okay. So if you look at the options, JA rho power 4 means according to that person R power 4 by 5. Answer is nothing but C. Okay. Yeah. So this is what you have in this question. Simple question again. Simple application of Ampere's law. Okay. And the process that you see here parallels with what we have followed in Gauss law also, but there the logic was d into 4 pi r square, because there you are calculating flux density into area. Here you are calculating what? Field intensity into length of the path that you are traveling around. Okay, is equal to, there it was nothing but total charge integration of rho s ds. Here total current, which is integration of j dot ds. Okay. Yeah. Next, this is very important. What is the expression of H bar and B bar because of some common current distributions? The first one we are taking is nothing but finite length line current. This was not so important in case of electrostatics, but rather very important in case of magnetostatics. Let's assume there is a current carrying conductor carrying a current of I. The length of this conductor is some finite length, and it's some rho meters away from the conductor. What is the value of magnetic field intensity? So this is the point of interest. At this point, because of this current carrying conductor, what is the value of magnetic field intensity? The angles made by the edges of the conductor with respect to the point of interest is nothing but theta 1, theta 2. So given this data, what is the expression of first of all h bar, and similarly what is b bar? Okay, and by the way, I'm sorry, I forgot to mention the relations in the beginning. Yeah, here b bar is related to h bar as b bar is equal to mu times h bar, where mu is mu naught times mu r, where mu r is nothing but relative permeability, and I believe all of you know what is the value of mu naught. Mu naught is 4 pi into 10 power minus 7 Henry per meter. Okay, so I forgot to mention this one relation. One more relation is nothing but flux. What is flux and flux density? What is the relation between both of them? Multiplication. Flux is equal to flux density into area. You can directly multiply them if at all flux density is constant. But we don't assume that flux density is to be constant, so we have to perform integrations. Instead of multiplication, we perform integration. Integration of b bar dot ds bar over the surfaces. So this is basically the phi m relation with respect to the flux density term, which is nothing but b bar. Okay, I forgot to mention these terms. So same story here also, that the moment you get h bar, how do you get b bar? As mu times whatever h bar you have becomes equal to b bar. So in this case, like in the previous case, in the electrostatics case, finite length line charge scenario, what was the expression of electric field intensity? Some expression of rho L divided by 4 pi epsilon rho, but instead of that here you are having rho L means their source, here source is nothing but current, I divided by 4 pi rho into the bracket term remains same, cos of theta 1 plus cos of theta 2, direction is nothing but phi cap. Phi cap means what direction? Circulating direction. So the magnetic field obviously circulates around the conductor, and hence I have taken the direction here as nothing but circulating direction. But understand, you have to find out the direction of magnetic field intensities by using right hand thumb rule. Okay, and into mu is nothing but b bar. And now a special case, this special case where semi-infinite conductor. So in this case, when you join the infinite end with respect to the point of interest, how much is this angle? Maybe this is theta 2 in this diagram. So theta 2 is how much? 0 degrees. What is this angle now? Theta 1. Theta 1 becomes equal to 90 degrees. Okay. So theta 2 is nothing but 0. Theta 1 is 90. So yeah, one of them is nothing but 0. Cos 0 is 1. Cos 90 is nothing but 0. Bracket term becomes 1. So we have the total answer as nothing but I by 4 pi rho times phi cap. And magnetic flux density is nothing but mu I by 4 pi rho times phi cap. Okay. Infinite case, both ends are at infinity. So in this case, both ends are at infinity. So means angles are how much? Theta 1, theta 2, both are 0. Cos 0 is 1. Second one, cos 0 is also 1. So bracket term becomes 2. 2 by 4 pi rho becomes equal to 1 by 2 pi rho. So in this case, we have 2 pi rho in the denominator. Okay. Direction remains same as compared to the previous case. Circular ring scenario, do remember this one again. Let's assume the radius of the ring is nothing but a. So in this case, when you apply right hand thumb rule, curl your fingers right now in the direction of current. The thumb indicates direction of magnetic field intensity. So in this case, magnetic field is coming towards you out of the page. Okay. So let's assume this is the point of interest. So what is the value of magnetic field intensity at this point of interest? The expression is given by I by 2a. There is no pi term here. There is a pi term here. There is no pi term here. And there rho is nothing but distance. Here also a is nothing but radius or distance between the current carrying conductor and the point of interest. Distance is nothing but a. But only thing is the pi term is missing here. So that is one way of remembering the formula. Okay. So semicircular ring scenario. In case of semicircular ring, the answer will be half of the previous case. In the previous case, circular ring, we have got the answer as I by 2a. Half of that is I by 4a. Okay. So that is the expression in case of semicircular ring current scenario. Okay. And lastly, infinite sheet current. So whenever you have infinite sheet current, the current density is given by, the magnetic field intensity h bar is given by, here h bar is given by k bar cross n cap by 2. Here n cap is nothing but unit vector. This is unit vector from sheet current, from the sheet current to the point of interest. To the point of interest, right? So this is what we have regarding infinite sheet current scenario. So let's look at the problems. Yeah, this is the most recent one we have got in 2023 only. Very simple question. Surprisingly, that was one of the toughest papers, and we have got one of the easiest questions from EMF. Infinite surface of linear current density K bar is given 5 amperes per meter. Direction is also given x cap. On xy plane, the current is basically flowing on xy plane. The magnitude of magnetic field intensity H at a point 111. So at some point, I don't care where the point is there. So anyway, so from this sheet to this point of interest, the sheet is nothing but xy plane, right? And where is the point present above xy plane? Maybe this is the point of interest. So means in the given scenario, what is n cap? N cap is nothing but from the sheet to the point of interest, I have taken a unit vector. So is it not in the direction of z only? Yes. So because of that, n cap becomes equal to z cap. Okay. So because of that, what is magnetic field intensity H bar? K bar cross n cap divided by 2. I want H bar at the point of interest, 111 becomes how much? Substitute the values. We have 5x cap. We have 5x cap cross n cap is nothing but z cap divided by 2. What is x cross z? X cross z is minus y. So we have minus 2.5 y cap. That's it. And what is the answer? Finally, you are supposed to tell only magnitude only. Only magnitude. So what is the magnitude of this guy? 2.5. That's it. And GATE 2023 electrical paper was one of the toughest papers for electrical branch. Though it was one of the toughest papers for electrical branch, if you look at this question, all we have is k by 2. The value is nothing but k by 2. K is 5. 5 by 2 is nothing but 2.5. Done. Okay. So very simple question this is. Right? No. It is not cos theta 2 minus cos theta 1. This is cos theta 1 plus cos theta 2, because I am taking the angles with respect to the edges, not with respect to the normal here. I am taking the angle with respect to the edges. Please notice very carefully here. Okay. The angle measurement is not done with respect to the the normal. And furthermore, I am not talking about electric fields here. This is magnetic fields. Okay. So this is the expression for magnetic fields along phi cap direction. Right? Yeah. This is one question that we generally solve in handouts also. So we have a current entering this particular hexagon like this, and this is a regular hexagon. I think somewhere it is given regular hexagon. Okay, this is a regular hexagon. Okay. So yeah, direction of currents would be like this. So how many conductors total we have here? Can I say 6 conductors? Yes. This is conductor number 1, 2, 3, 4, 5, 6. And I want what is the value of magnetic field intensity at the center. Center is nothing but, let's assume O. So I want magnetic field intensity H bar at point O becomes how much? H1 bar plus and so on plus H6 bar. But if you notice, all the 6 conductors produces magnetic field intensity in the same direction. In what direction? So if I curl my fingers in the direction of loop, right hand, so what is the thumb pointing out? Thumb is pointing out into the board. So because of that, this becomes equal to 6H1. Since regular polygon, all the conductors are identical and they produce the same amount of magnetic field intensity at the center. So 6H1, direction is nothing but cross. So what is H1? Each of these conductors, can I consider them as nothing but finite length conductors? Yes, they are conductors of finite length. Okay. And in our derivation that we have done or expression that we have taken, okay, so I have written the formula always in terms of this parameter. This was called as rho. In the given case, do you have this rho value? No, we don't have this rho value. But I know that this is a regular hexagon. Side length is nothing but 1 meter. Side length of this hexagon is nothing but 1 meter. Means how much is its value? This is 1 meter. By using this, can I find out what is the bisector length here? This is equilateral triangle obviously, because regular hexagon means total angle is how much? Total angle is 120 degrees. Means what is this angle? This is nothing but 60 degrees. Angles made by edges with respect to the point of interest are nothing but 60 degrees. And furthermore, what is the value of rho from this diagram? From this diagram, okay, rho value becomes equal to, see, total length is nothing but 1 meter. How much is half length? Half length is nothing but 0.5 meters. And this is how much? 60 degrees. I can take tan 60. What is now tan 60? Tan 60 is nothing but rho opposite side by adjacent side. Rho by 0.5 is equal to tan 60, which is nothing but root 3. So rho becomes equal to root 3 by 2. Root 3 into 0.5, root 3 into 0.5 is nothing but root 3 by 2. So we have the value of rho also. Now I have everything to get the answer. 6 into, because of each conductor, what is the value of magnetic field intensity at the center? The formula, I by 4 pi rho cos of theta 1 plus cos of theta 2. Okay, and direction is what? Cross. Direction anyway in the given problem is not required, but still good to know it is nothing but cross. Substitute all the values. 6 by 4 is nothing but 3 by 2 into current. How much is the current flowing in the conductor? 1 ampere. So this is 1 ampere divided by 4 pi into rho. We have been magnetic flux density, sorry. You are supposed to calculate B. So if it is B, same story, B1 bar and so on, B6 bar, 6 times B1 bar, mu I by 4 pi rho. So mu corresponds to how much now? 4 pi into 10 power minus 7 divided by rho. Rho is indirectly given, rho is nothing but, we have to do some geometry calculations and finally we have got it as nothing but root 3 by 2. Direction is what direction? Cross direction here. That's it. If you do the cancellations, here we have 4 pi and 4 pi is gone. The 2 here and the 2 here is gone. Root 3 cancels out 3 here, root 3 times. And finally we have to get the answer in terms of what units? Micro Tesla. You have to get the answer in terms of micro Tesla. So we have root 3 into 10 power minus 7 as the answer. So this is root 3 into 10 power minus 7. So means 1.732 into 10 power minus 7 or wait a minute. 0.11732 micro Tesla. Okay, so this is the answer, right? Okay, not a tough question again. Yeah, try to solve this question now. You have two identical copper wires W1 and W2 placed in parallel. Currents I and 2I respectively. So in W1 currents 2I in opposite directions. Okay, in opposite directions. So if I consider the current here as nothing but like this, the other conductor is nothing but opposite direction. If the two wires are separated by a distance of 4r, okay, so total distance is nothing but 4r, means how much is this distance right now? This distance is nothing but 4r minus r, which is nothing but 3r, So then the magnetic field intensity between the wires at a distance of r from W1, so they have given the diagram anyway, okay, is how much? So total distance between them is given as 4r though. This is 4r and one of the distance is nothing but r, then the other becomes definitely 3r. So here using the formula is not a big deal, but rather understanding the direction of magnetic fields is very important. And we find out that by using right hand thumb rule. If I am holding the conductor 2 with my right hand in such a way that thumb is pointing out in the direction of current, then what is the direction of magnetic field intensity? Into the board, right? Into the board means cross. So place or write that cross. This is cross. Because of whom? Because of conductor 2. So because of 2 it is nothing but cross. Now forget about 2. Come back here now. Okay, I am holding the conductor 1 with my right hand in such a way that again thumb points out in what direction? In the direction of current. Then please notice at this point, at this dotted line is the point of interest. What is the direction of magnetic field intensity? The direction of magnetic field intensity is nothing but again into the board. So into the board means cross again, cross even because of conductor 1. So because of both conductors, direction is nothing but cross only. Means what? You can directly add the magnitudes. Okay, so this is what you are supposed to first of all identify. Should I add the quantities or should I subtract the quantities? Okay, so in this case, we are supposed to add the quantities. Okay, so whatever is H at the point of interest we require, this is simply now H1 plus H2 directly. I am adding both of them. Direction is nothing but cross. What is H1? H1 is I1 divided by infinite conductor. Nothing is mentioned means, were you mentioned infinite conductor? No, it is not mentioned that this is infinite length conductor, but still like I have told, if nothing is mentioned, we always supposed to line charge or line current no matter what, both cases. Okay, we are supposed to assume that they are nothing but infinite length scenario. Okay, so in that case, what is the formula for magnetic field intensity? H only they asked, no? No, they asked B, they asked B. So B I want. So they asked B. So B bar at point P becomes how much? This is nothing but B1 bar plus B2 bar, which is equal to, in this case, B1 plus B2 times cross, because both are in the same direction. What is B1? I1 by 2 pi rho 1 plus I2 by 2 pi rho 2. Okay, and I can nicely add the magnitudes. Okay, what is I1? I1, the current flowing in the first conductor is nothing but I. So that is nothing but I. So this is I divided by 2 pi rho 1. What is rho 1? Rho 1 is equal to distance between, this R corresponds to basically rho 1, distance between the conductor 1 and the point of interest. And distance between the second conductor and point of interest is nothing but rho 2. This is nothing but rho 2. So rho 1 is R, rho 2 is 3R. So this is R plus I2 is 2I divided by 2 pi 3R. Okay, both are in the cross direction only, cross. So would become how much? I by 2 pi R, if I take common, or can I take I by pi R, I can take common, no, because 2 is gone here. So I by pi R I can take common. Then we have here 1 by 2. Here we have 1 by 3, 1 by 2 plus 1 by 3 cross, which becomes equal to 1 by 2 plus 1 by 3 is how much? LCM is 6, 5. So 5 I by 6 pi R cross. Okay, so if you look at the options, pi and I'm sorry, I'm always used to mu notation, H notation. There will be mu term also in all the cases. Okay, so 5 mu I divided by 6 pi R. So this is what we have regarding the next one. Okay, next. This was one question that we have got in 2020, 2-mark question, electrical paper. Good question though. Now here, you have been given that this distance is equal to 1 meter. You have a square loop here. Side length is nothing but 1. So this is 1 meter and this is also equal to 1 meter. Okay. You are supposed to tell how much amount of magnetic field intensity crosses this particular loop. That is what is the question. Again, if you are good in coordinate geometry, answering this question is not at all a big deal. All you will assume is nothing but, okay, this is Z. So current is flowing in Z direction. Okay, some magnitude is given to you. We don't care for now. So then what is the expression for H bar? H bar becomes equal to, like I have told, whenever current is flowing in Z direction, magnetic field is in phi direction. So expression is I by 2 pi rho, direction is phi cap. That's it. You take this. The moment you get this expression, more or less you are done. What you are supposed to calculate? The mutual inductance. So some mutual inductance we are supposed to calculate. But to calculate mutual inductance, you are supposed to calculate flux. Calculating mutual inductance in this problem is not a big deal, okay? But calculating flux is very important. So let us see how to calculate flux. To calculate flux, we require flux density. What is flux density now? This is mu times h bar, which becomes equal to mu I divided by 2 pi rho phi cap, okay? Yeah, now by using this, can you calculate the flux? Magnetic flux crossing through this particular loop becomes equal to, this is integration of B dot ds. Now this is integration of what is B bar? B bar is along phi cap direction. Along phi cap direction, what is the value of ds bar? So this is now mu I divided by 2 pi rho phi cap dot d rho dz rho cap, phi cap. So along phi cap direction, what is the differential area? The differential area along phi cap direction is nothing but d rho dz. You are supposed to multiply lengths along rho and z directions. Rho length is nothing but d rho, z length is nothing but dz. Multiply both of them, you get d rho dz. Okay. Now let's. I'll continue that here. Okay. Now what is the value of phi m? Phi m becomes equal to now mu I by 2 pi. I can take it outside. I'm keeping that outside. Now we have two integrations. One is nothing but integration of dz. What is the integration of dz? Z. And one more is nothing but integration of d rho by rho. What is integration of d rho by rho? ln of rho. So the second one is ln of rho. Now limits. You are supposed to take limits from where to where. Since I am concerned only about this loop, I will take only the limits for this loop. Okay. Now this is the lower limit for rho. Rho starts from where? Rho is the radial distance from the z axis. So this is the first one. How much is its value? D. And how much is this value? This is the second limit. Starting from here till here, I am going. So this is the initial point for rho and this is the final point for rho. And this becomes d plus a. Okay. So for rho, the limits are nothing but from d to d plus a. For z, start somewhere. I don't care where you start. Maybe, this is the starting point for you. Maybe z naught. And this is the ending point then. How much is the ending point? How much is the vertical distance? Vertical distance is nothing but a. So this is z naught plus a. So here the limits are, lower limit is z naught. I don't know what is z naught. You can take 0 also if you require. And upper limit is nothing but z naught plus a. Okay, when you substitute the limits right now, what is the answer you are having? The answer is nothing but mu I z plus a minus z is nothing but a divided by 2 pi. Ln of d plus a minus ln of d is nothing but ln of d plus a by d. Okay, this is what you have regarding flux phi m. Now what is the formula for inductance? Some of you already know the formula for inductance. Inductance L becomes equal to flux linkages, in this case divided by total current. So phi by I, if you take phi by I, this becomes equal to mu A divided by 2 pi ln of d plus A divided by d. Substitute everything. Mu by 2 pi is nothing but 2 into 10 power minus 7. So this is 2 into 10 power minus 7 into A is equal to 1 into ln of d and a both are nothing but 1. 1 plus 1 is 2 divided by 1 is nothing but 2. So ln of 2. So when you take ln of 2 is nothing but 0.693 I believe. If you see ln of 2, what is ln of 2? 0.693, yes, into 2 is 1.386. So this is 1.386 into 10 power minus 7 Henry. Okay. And I think you are supposed to get the answer in terms of micro. I'm not wrong. Nano, in terms of nano. So in terms of nano means what? 138 into 10 power minus 9. Okay. So nearly this becomes equal to 138.6 into 10 power minus 9 Henry, which is also equal to 138.6 nano Henry. Okay. But yeah, the last part is not a big deal. L is equal to phi by I. All you have taken is the ratio. There is no great calculation here. This part is very important. How do you calculate phi? And see, phi calculation is also not a big deal, because the moment I remember what is the direction of magnetic flux phi cap, then I am taking here ds bar also along phi cap direction. Yesterday we have seen this, right? So ds bar along phi cap direction is multiplication of lengths in rho and z directions. That's what I have taken, and I substituted the limits from the diagram, got my answer. Okay. So this is regarding the second part of magnetostatics. First part of magnetostatics is Ampere's law. Ampere's law is something that you have to remember no matter what. Second part is B bar and H bar due to some of the common configurations like finite length conductor, semi-infinite length conductor, infinite length conductor, and lastly ring current scenario. Okay, all these 4 cases you have to remember. Very important, you get a lot of questions on this. Okay, and questions are pretty simple. All you have to do is nothing but use formula and observe the directions properly. Yeah, you will get your correct answer. Okay. Next is nothing but we look at the solenoidal nature of magnetic fields. So yeah, magnetic field always flows in closed path, and due to which there is no net source nor net sink of magnetic fields. Okay, so here in this case always flows in closed paths, and because of which there is no net source, no net sink of magnetic field, and hence magnetic monopoles do not exist. Because if there is a magnetic monopole, there would be either net source or net sink. So in this case, we neither have a net source nor a net sink, means magnetic monopoles do not exist. And hence, how do magnetic poles exist? Always they exist in pairs. So there is always a north pole associated with the south pole and vice versa. Whenever there is a north pole, pakka there should be a south pole as such. Okay. And because of this reason, if I calculate the flux coming out of any closed surface, the magnetic flux coming out of any closed surface becomes equal to 0. Okay. So magnetic flux coming out of any closed surface is nothing but 0. So means mathematically, flux coming out of any closed surface means what? Flux is integration of b bar ds along a closed surface S becomes equal to how much? 0. So that is what we have taken here. The closed surface integration of magnetic flux is nothing but 0. Upon applying divergence theorem, when you apply divergence theorem, what will happen now? So this becomes equal to integration of del dot B dV, and this also becomes how much now? 0. So when will this become 0? Whenever divergence of B bar becomes equal to 0. So in case of magnetic fields, divergence always becomes 0 no matter what magnetic field you take. Static, time varying, irrespective of that, always divergence of a magnetic field becomes pakka equal to 0. So for a magnetic field, whenever we say it is solenoidal, we are meaning three points here. First point is nothing but divergence always is 0. Closed surface integration of any closed surface you take always is pakka 0. And the last one is basically there always exists a vector potential which defines the magnetic fields as nothing but this magnetic flux density is equal to, this is our magnetic flux density. Okay, now that becomes equal to curl of the vector potential. Okay, this A bar term that you see is basically the so-called vector potential. So whenever examiner gave you vector potential, indirectly they also gave you the information of magnetic flux density, which is nothing but B bar, because you can always calculate B bar by simply taking the curl of magnetic field intensity, magnetic vector potential. Okay. So let us look at a few questions on this. One simple question, we have been given B bar, and that B bar is nothing but flux density. You have the units also to confirm that flux density, and this is basically a magnetic field. Okay, so this expression is basically magnetic field, and the property of a magnetic field is nothing but magnetic field always is solenoidal. This is always a solenoidal field. So since it is solenoidal, what happens? Divergence of this field becomes 0. Okay, so because of solenoidal nature, divergence is 0. What is the divergence in case of rectangular coordinate system? Differentiate x term with respect to x. Differentiation of 4x with respect to x is nothing but 4. Anyway, we'll write the formula also. So divergence expression here is nothing but dou bx by dou x plus dou by dou y dou bz by dou z. Okay, so the summation of all these guys is nothing but 0. So first one is nothing but 4. Differentiation of 4x with respect to x is 4. Differentiation of 2xy with respect to y is nothing but 2k. and differentiation of 8 with respect to z is 0, becomes overall 0. So k is equal to 2k is minus 4, k is nothing but minus 2. This was in 2013. Please look at, this was asked for 1 mark though. Same kind of a question we have got in 2024 also. 2024 also we have got the same question. So look at least model, and it was a 2 mark question. This was a 2 mark question that we have got in 2024 electrical paper. The given equation blah 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 magnetic field. Okay, this is what you are supposed to see, which is nothing but h bar in the spherical coordinate system again blah blah blah, and finally find the value of p in the equation. Again unknown value is given, h bar is given or b bar is given, unknown value is given, and you are supposed to find out the unknown value. What is the logic there? Yeah, the logic is nothing but since this is magnetic field, okay, what we can understand now, divergence is nothing but 0, because magnetic field is always solenoidal. Okay, but only thing is now you have to remember the formula for divergence in spherical coordinate system. Okay, that was rectangular coordinate system 1 mark, spherical coordinate system, hence it is 2 mark. Okay, what is the formula for divergence in case of spherical coordinate system? Okay, so this is basically 1 by multiplication of scale factors r square sine theta into dou by dou r of r square sine theta times hr plus dou by dou theta of h1 h3, which is r sine theta of h theta, plus the last one I don't even have to take because h phi I only have r cap term as well as theta cap term. There is no phi cap term, and hence the last part is nothing but 0. So this overall becomes equal to how much? 0. Okay, now you have hr as well as h theta to substitute. Please do it. So this hr is equal to p cos theta divided by r cube. So this is p cos theta divided by r cube. And what about the other guy? This is sine theta divided by r cube. So h theta is nothing but sine theta by r cube, right? Yeah. Next, I can send this 1 by r square theta to the other side. Then what do we have? We have sine theta here, cos theta here. Take it out. So we have sine theta, cos theta, and we have a p here, p, and then r square divided by 1 by r cube becomes how much? 1 by r. So dou by dou r of 1 by r becomes how much? Minus 1 by r square. Yes. So this is minus 1 by r square because of differentiation. Then what about the second term? R by r cube is nothing but 1 by r square. So this is 1 by r square. And then here we have sine square theta. What is the differentiation of sine square theta with respect to theta? So differentiation of sine square theta is nothing but 2 sine theta. And differentiation of sine theta is nothing but cos theta. Cos theta becomes 0. Okay. What are the common terms? Let's take the common terms. Sine theta cos theta, sine theta cos theta gone. 1 by r square, 1 by r square. I am taking them common, throwing them to the other side. Then finally, what we have is nothing but here p, which is minus p, plus 2 becomes 0. There you have only 2 here. Means p becomes equal to 2. That's it. So I got my constant value. So the model, if you notice, it's not a new model. So this is simply old model only, but rather asked in spherical coordinate system. Okay, spherical coordinate system. So, okay. So here, in all these problems, if you notice, we have less of EMF, but rather more of vector calculus. That is the reason why yesterday I have dedicated entire time to only vector calculus. Okay. 2 Pavani, it's not minus 2, it's 2. Yeah. Again, see, latest question only. Which of the following vector functions represents a magnetic field? So all you have to do is nothing but verify all the options. Okay. Take the divergence of the first option. del dot B. Let's assume in all these cases del dot B we have. What is del dot B? Differentiate the x term. Differentiation of 10x is nothing but 10. Differentiation of minus 30z with respect to y, 0. Differentiation of 20y with respect to z, 0. So finally what is the answer? 10. Is it a 0 value? No. So option A is not the correct answer. Every time take divergence. If it is 0, correct answer. If it is not 0, wrong answer. Next case, again divergence. Take divergence of this field. Differentiation of x component. X component is 10z, 0. Differentiation of 10z with respect to x becomes 0. And differentiation of 20y with respect to y is 20. Differentiation of minus 30z with respect to z, minus 30, answer is minus 10. And then, so yeah, what is the answer? Answer is nothing but 20 minus 30, not 0, so not a magnetic field. Third option C, if you take divergence here, del dot B, differentiation of 10y with respect to x, 0. Differentiation of 20x with respect to y, 0. And differentiation of minus 10z with respect to z, minus 10. Answer is minus 10, not 0, not the correct answer. Last case, differentiation of 10x with respect to x. 10x with respect to x is 10. Differentiation of 20y with respect to y is 20. Differentiation of minus 30z with respect to z, minus 30. Answer is 0. Correct answer. Okay. So wherever we get answer as nothing but 0, yeah, that is nothing but our magnetic field. If it is not 0, not a magnetic field. So these kind of questions can be asked as MSQ. Okay. So this can be asked as MSQ. Okay. I want you guys to solve a couple of more questions. There are 2 more questions in fact, I think. Yeah, these are 2 more questions. And I want you guys to try out these 2 questions. Okay. So with this, I'll close the session. Okay. I think we have covered enough content in case of electrostatics as well as magnetostatics. Yeah, I agree that we haven't covered every topic. Specifically, we have missed 2 areas. One is inductance capacitance calculations. I agree it's a very important area. And the other is boundary conditions, not so very important area. We don't get regularly questions on boundary conditions in GATE exam. But yeah, capacitance, inductance calculations, we do get it every year. The reason why I have skipped that is nothing but anyway you will learn about inductance calculations in power systems as well as in the at least capacitance calculations. Inductance calculations you also see in machines, in power systems and machines. Inductance and capacitance calculations you do see. So that is one reason that I didn't discuss that particular topic. What you study, don't study there, is what we have discussed here mainly. Okay. Even the reason why we studied coordinate geometry is because you don't study coordinate geometry with respect to spherical and cylindrical coordinate system in mathematics. Okay. So coordinate geometry and vector calculus we have seen not just in terms of rectangular coordinate system but also in other coordinate systems. Okay. So yeah, I hope the session is useful for you. I hope the session is useful for you. So we'll with respect to electrical guys, yeah, this will be our last session. We'll meet again in digital electronics. Okay. With respect to EC students, we'll again meet in EMTL portion. Okay. We'll again surely meet in EMTL portion. Right. Thank you. Thank you for joining the session. And like I've told, I hope this session is useful for you guys. Yeah. Good night everyone, and all the best for your exams. Do well, maintain a positive attitude in the coming days. In all the coming days, maintain a positive attitude. Believe that you can do it, and yeah, then definitely you will be able to do it. Okay, so you always have to believe yourself.